So good morning guys, welcome to our Optistruct nonlinear training. Hope you can see my screen and my voice is loud and clear. Right, so this is what we have for our 2 days of training, right? Basically, we are going to touch on the topic of nonlinear, so we will first understand what are nonlinear problems. And when we go through chapter 1, you'll see that nonlinear is actually just consisting of mainly 3 categories. First, you have nonlinear material, then you have nonlinear geometry, right? And because of this nonlinear geometry, sometimes you need to consider nonlinear loads as well. So these 3 and 4 are related. And the final nonlinearity that we deal with is actually the context. Okay, so that's the nonlinear boundary, where the boundary is changing. So the context is the nonlinear boundary. Okay. So basically, we're going to deal with nonlinear material, geometry, and context. And then how do we use that for in this case here, right? So for pretensioning and also using the pretension in the first step and consider the pretensioning and the tightening for the second step, right? So we have that capability here, right? So with online training now, you can see that we actually cut down the training time. So what I have during these 2 hours presentation is mainly on lecturing, right? And you'll be probably reading my notes and you'll be hearing audio, visual, right? And I also do some demonstration throughout my training. So you probably retain 30% if you just sit here and listen. But if you start doing it, so if you download the models and you practice on the exercise after the training, you probably remember 75% of what I've learned, what I've taught. So I would encourage you guys to download the materials and then go through the exercise yourself after my lecture here. And if you start to teach the others about what you have learned today, you probably remember 90%. Okay, so make use of what you have learned today and practice it. Okay. Right. So this is what we're gonna go through in chapter 1. And let's just start off with the theoretical part. I guess you guys are already clear when do you determine that you need to go from linear solution to a nonlinear solution, right? So for linear elastic solution, you probably see that your displacements are normally small or can be totally ignored, right? The material is still behaving linearly, so that means your deformation is happening in the elastic region. Okay, there's no change in boundary conditions, means that it doesn't move much. That made it move to a new area where there's a new boundary condition or new contact, right? So normally the boundary conditions are fixed, so you don't have any change in boundaries. Okay, and the loading is normally constant with respect to time. So this is where you actually perform linear solutions. Okay, but when the problem becomes non-linear, you probably see that the material may not behave already, may not deform, or may not just work in the linear or in the linear elastic region. It probably has gone into exceeded yield and it's gone to the plastic region. So that's where you need to consider non-linear. Like for example here, this is a snap through, right? So you press on the load. And then you increase the load until it suddenly snaps and it bends downwards, right? So this is a nonlinear problem because there is a change in geometry already, nonlinear geometry, okay? And also there's another condition where there's contact, so you're familiar with that. So when you have this kind of situations, you need to consider nonlinear solution, right? So nonlinear geometry, nonlinear is normally associated with large displacement, right? Large displacement, large rotation, or if your strain is very large, right? Sometimes your displacement might be small, but the local strain might be large. So then you need to consider nonlinear as well, all right? And then of course, if there's a buckling, then it's definitely a nonlinear geometry situation, okay? Yeah, so this is an example of a geometry nonlinear. If this is the same model, while I use a linear analysis and I load it, right? Let's say the load is very large. For linear, it doesn't consider that this buckling here, so it just displays this in this. Let's say this is x direction. Okay. So let's say if this is x, right? Z and y. So if this is x direction, the load is in x direction, the displacement will also be in just x direction if you're solving this with using the linear solutions, right? But if you consider nonlinear, especially if you turn on large displacement here, you see that you actually bend up. So with different kind of parameters that you set, you actually get different results. Okay, so you need to understand your load case, whether it's gonna whether the load that is applied is gonna give you a large displacement or whether it's just a small displacement. Okay, so then you need to decide whether I can solve it using the linear static or I need to use the nonlinear static. Okay. Now, geometric nonlinearity can also be applied when the problems are with small strain. Okay. But if there are other nonlinearities that is being applied. So for example, if you have boundary conditions and nonlinear material, you can also turn on the large displacement. Okay. So this will capture the the geometry change better compared to when you're solving with a small displacement solution, right? Yeah. So this example of large displacement. If you turn on large displacement, you will see that sometimes the differential is actually not very small, right? Because if you use a linear analysis, the deflection of this thin plate here might be over predicted. Okay, so when you let's say if you're comparing this against testing and you find that the displacement is too large compared to the testing when you're solving linear analysis, then you might want to turn on large displacement. So when you turn on large displacement, you automatically perform a nonlinear analysis already, right? So yeah, because in large displacement we capture this in-plane membrane stiffening, and sometimes it's important, especially if you're dealing with thin plates, right? The second nonlinearity has to be with materials. So this is pretty obvious. If you just say you are expecting your parts to perform exceeding the U point, then you need to consider the nonlinear material. Okay, so if you're talking about elastoplastic material, or if you're talking about hyperelastic material, right, then you definitely need to consider the nonlinear materials. Okay, so what we have done with the previous linear analysis is we only deal with MET1, which is the linear isotropic material. But now later on, you see that we actually need to define the plastic region using the MET-S1 card. Okay, so it is under this MET1 here, and you see we actually need to define the this portion here of the curve. Okay, so yeah, you can either use if you have the stress strain curve, the exact stress strain curve, then you can actually use the stress strain curve data from the material testing. Otherwise, you can also build in the curve here using the slope and then the yield point and so on, right? Yeah, so here is an example where there's a nonlinear material problem. The displacement here might be very small, okay, but then there's a localized plastic strain here. So if you want to consider localized plastic strain, you need to consider nonlinear material, right? And the third nonlinearity is to do with boundary change here. Okay, so for example, if the gear is moving, first there is in some areas they might not have any contact at the beginning, but then as the time progress, you see that suddenly it has now a contact with the bottom gear, right? So when you deal with this boundary change, you have to consider context, right? So for context, um, later on, we will also touch on context. I'll teach you how to set it up. And comparing to Radios, because you guys are familiar with Radios, Radios has auto contact. So in Optistruct, we do not have auto contact yet. So you need to define contact pairs. Okay, but there is a method to do auto search for the contacts, but then when the card is being written, it is still done in contact pairs. Okay, so for implicit, we normally deal with contact pairs because you see later on implicit actually takes a longer time to converge, and if you set up your contacts correctly and properly, then the convergence issue will be lesser. Okay, so normally when there's a convergence issue, it's normally deal with context. Right. So what we're actually solving for nonlinear problems, we are solving, of course, still solving the motion equation. There are two methods to solve it. First, there is that implicit method, which we are using now. Okay, and then there's the explicit method, which is using the for Altair is using Radios, but we in Optistruct we also have the explicit solution already. Okay, but it's still it's still in development. We are adding more features version by version. It's not that fully matured yet, but if you let's say you want to perform a drop test in Optistruct, we can do it already. But if you want to consider the damage models, because in Rogers we have a lot of damage models, right? So that is not fully supported yet. Okay, so if you still rely a lot on damage models, then please stick with Radios. But if your materials are simpler, you don't need to go to those damage models, then you can consider Optistruct, because then you have a single model that can run for implicit and can also run for explicit. Okay, so that's the benefit. That's the purpose of we creating Optistruct explicit. It's not to fight with our own radios. It is mainly to help some customers because they do not want to have two models for two different load case. They just want to have the same model running for Optistruct, because Optistruct you can run for static, you can run for NVH, right? And then you can run for you can run for fatigue, and now you can run for explicit for drop tests also. Okay, so when they have a single model, it's easier to manage for them. Okay. If you're considering whether you want to solve it using implicit or explicit, because we have the both solvers available for you. Normally for implicit case, if you're solving any static case or elastic, even plastic, then that's the best solver for that, right? But if you want to consider rupture, like cracks and so on, you want to see how the crack propagates and so on, then probably explicit is better. Okay, so even dynamic events, yeah, if you want to solve dynamic events, high-speed events, then you probably need to go to explicit. Okay, of course, cost versus complexity. For linear static here, you see that the cost of solving it in explicit is actually very high, but for us, you just solve within a few minutes, right? So that's where we consider to use implicit solution. Okay, so for nonlinear, it's probably working around nonlinear static. It's probably working around this region here as well. Okay, so it's easier to it's faster to solve in Optistruct rather than going to Radios. Okay. Right. So these are our nonlinear solution that we have in Optistruct. There's a nonlinear quasi-static, nonlinear transient, nonlinear explicit, and then nonlinear steady state for heat transfer. Okay. Mainly we're going to focus on the NL stat here. Okay. And mainly deal with setting up contacts, materials, and also how to turn on the large displacement here, right? So a bit on the nonlinear static analysis, NLStat. It's mainly used to solve quasi-static problems, means with low or negligible initial force, means that it doesn't change much with respect to acceleration and also constant velocity, right? So there's no acceleration. If it's a very slow and a constant velocity, very slow especially, then you can consider that problem has a quasi-static, right? Or of course static problem as well. Okay. Right. So if you're considering those rotational fans, right? Rotate the fan rotating at constant velocity, then you can also consider that to solve it in using a nonlinear static analysis. Okay. Yep, we are using the Newton-Raphson method to solve the motion equation. And the interesting thing here with time is because what we're solving here is actually static problems. Like it's either quasi-static or static, right? So, but right, it doesn't change. The loading doesn't change with respect to time. Okay, but in most of our especially those time increment that's written out during the calculation. Okay, during the solving time, you see that a lot of documents will mention time. So time solving at time equals to 0 or time equals to 1. You probably see those time steps, right? When we mention time steps in nonlinear static, we're actually referring to load increment. Okay, so let me show you what it means. If I can just find one of the files. We can't see it right now, but let me just find the files first so I can show you guys. Let me see this one. All right, so let me just share the screen. Right, so I think you can see this file here. So when we are monitoring for nonlinear static analysis, you sometimes this is a dot monitor file where we can actually have a glimpse of what's happening for each iteration. Okay, so you see that for nonlinear stat NL-stat solution, the maximum time increment is actually always 1. Okay, so even though we mentioned time here, right? We mentioned time here. What we actually mean is when time is equals to 1, the loading that we apply, let's say we are applying 500 Newton, the loading now is actually 500 Newton. So when time equals to 1, that means you're applying full load. Okay, so all these increments of it are actually a percentage of the load. For example, if let's say time equals to 1 is actually full load where I apply 500 Newton, 0.1 is applying 50 Newton. Okay, so here is 50 Newton, and then here we increase 100 Newton, and so on. So when you see time here, it doesn't really, you don't really link it to time. So if you're familiar with radius, then radius is real time. But here it's actually when we mention time, it's actually a time load increment, not really time, right? So you see, yeah, you see that the subcase time here, and then there's the load factor. So what we really mean is actually the load factor, okay, or the load increment, okay. So there's not really a time in the NL-stat analysis. All right. So just take note of this one. So during my lecture, I might be mentioning time. When I mention time, it really means the load increment. All right. So I'll go back to my slides. Okay, so just take note of that. Right, and when we say, when you see there's a time, the termination time of 1.0 means that we actually apply 100% of the load. So, yeah, just remember that. Right, so we are using the Newton-Raphson method to actually solve this this motion equation, right? And we are actually, so for each step, each time step, we are actually considering these three here. We always check these three errors when we're solving each time step. Okay, so we check for displacement, we check for the load, and also check for the work. And we make sure that it doesn't exceed the tolerance, default tolerance that is set here. Okay, if it does, then we actually cut back. We can cut back, and then if you're dealing with contacts, then we'll fix some of the contact elements. Otherwise, we will also change the time step. So we can either change the time step, solve it with a smaller time step, or we change the context if your model has context, right? So we deal with those two when we are trying to achieve a convergence. So all these are done internally, and you have the option to change the tolerance set that is set here as well. Okay, but I would advise you not to change this first. Okay, sometimes you might see that your problem cannot be solved because it's always failing this displacement error here. Okay, so let's say if I increase this, instead of 1e minus 3, I set it to 1e minus 2. Of course, then it's easier to solve and you get a convergence, but your solution might not be correct. Okay, so don't change this default tolerance first. Okay, instead look at your model, see what is wrong, if there's any mechanism that you need to fix, if there's any contact that you need to fix. Okay, so look at the model before you changing any of these tolerance here. Okay. And yeah, so this is a example of the cards that are related to the nonlinear static analysis, NLStat. You see that this normally we will define NL out, this NL pump. NL pump is a must. Okay, so let me just show you. All right, so this is a must. Okay, this is optional. Yep, NL pump here, this is a must, this is optional. Okay, so NL out just defines how frequent we want to output our results. Okay, so that's NL out. Okay, it deals with the output results. NL pump is a parameter that is needed when we are solving with the nonlinear static analysis. So NL pump is a must. We need to define this to activate the NLStat solution. NL out here is actually optional. If we do not set NL out, of course, then what solution is being written out? We will of course write out the solution when time equals to 0, that means initial, and also when time equals to 1, when it's the final. Okay, so you don't really get the incremental in between. If you want to look at the incremental results, what's happening in between 0 to 1. So remember, 0 is when your loading is 0, 1 is when your loading is full load. Okay, so if you want to see what's happening in between 0 to 1, you need to output NL out. You need to write this NL out and then request for the output. All right. So NL pump card is the parameter for the NLStat analysis. So all these cards, this card is needed. Normally what we define is the number of increment that we want, or DT, initial load increment. All right. So let's say time equals to 1.0 is your full load, right? And here is I normally set initial load increment here to be a certain value where I can achieve convergence in the first step. So some models, they are very sensitive. they might not be able to jump to 0.1 or 10% of the loading in the first step. Okay, so this dt here is the time increment for the first step, right? And if your model is very unstable, you cannot solve probably with 0.1, right? You cannot achieve convergence at 0.1 time step. So then you might want to consider to start with a smaller time step, say 0.01, right? So pardon me if I use time step and load increment. In NL step analysis here, time step is equals to load increment. So when I say time step, I'm actually referring to load increment. Okay, so if your solution is highly unstable, you cannot solve with initial time step of 0.1. You might want to go to 0.01. Okay, for the initial time step. Of course, over the time, if you find that we can achieve stability already, the model can actually run with a higher time step. So I'll teach you how to control that as well. Okay. And yep, so you either set dt here or number of increments, Ni and C. If you set both, if let's say dt set to 0, okay, we'll use Ni and C here to actually calculate the time step. Okay, but if you set both, then dt here, if let's say this is not 0, if dt is 0.01, then we actually use this 0.01. Okay, so it will actually sometimes override each other, right? So I normally just set dt here instead of using NINC. Yeah, basically this is controlling the time step. I don't. You see later on that here when you even though it's considered number of increments, you might think that it actually controls the time step, but because NL pump is not used for the output, right? The output is actually used in NL out. Okay, so the time step that you want to output is actually controlled in NL out. If you want to look, let's say if I want every results to output at 0.1, 0.2, 0.3, and so on, setting is here would not actually affect that. So we actually still use the NL out to control the outputs. So rather than setting NINC, I normally set in the NL out. Okay, but what I normally do is I set this dt here, initial load increment, especially if my model at the beginning is very unstable. All right, so that's more important. And you see this, you get to change this as well. Okay, so these three cards here, these are the default tolerance for the convergence check. So one for displacement, and then for load, and then for work. Okay, so if you want to, yeah, all this has been looked earlier. These all have their own default tolerance. If you want to change any of them, you just come and change the values here. Okay. All right. Okay, so this is the explanation of NINC and DT. Okay, so you can use both of them to control the time step. Actually, both of them will control the initial time step. Let's say if you didn't set DT is blank, or if it's 0, then we'll use the NINC that you have set to control the initial time step. Right. So yeah, you can use either one of them. Right. Yeah, so here's a table of supported 1D elements that is also involved for the 3 non-linearity. Okay, so even a control like non-linear material using CLS will not have effect. It's still just a linear element. Okay, but if you use C-bush, then there's an effect. Okay, so this is just a table for you to refer. Yeah, basically we support all, right, except for torsion here. Material wise, CELAS, there's no non-linear material. Okay, and C-rod also, right? Actually, CELAS doesn't have material, so whether it's linear or non-linear, it doesn't have any effect. All right, and then for shell and solid elements as well, So if this is more important for you guys, if you want to consider nonlinear geometric, let me see, somebody's coming in. All right. If you want to consider nonlinear geometry or nonlinear material, make sure you're using first order. Okay, so second order shell elements will not work for nonlinear geometry and nonlinear material. Okay, so just take note of that. Right, so as we learned earlier, NL palm is needed, is a necessary card for running a nonlinear analysis. Then NL out is the optional, where we control the output. Okay, then there is now a NL adapt. Okay, so NL adapt is this is also optional, but this is a card that can help you to achieve convergence better. Okay, so there are a few parameters here that you can actually set. Right, actually all these parameters here, they can actually set to help you achieve convergence better. Okay, especially this stabilize here, right? Static stabilize. So if your problem is highly unstable, for example, if your problem is a buckling problem, it's a buckling analysis. Buckling, as you know, is highly unstable. So if you want to have stability to your run to help it achieve convergence, then you can actually apply a stabilizer. Okay. And then apply stabilizer. The value here that you apply is actually a factor of the. Let me show you from the. All right, and I can see my screen. Let me just share my screen again and open NL Adapt for you. Okay, so so this and the NL Adapt card, you see, I'll explain the rest later, but most important is this stabilize here. So this applies the static stabilized energy, okay? And the value that you put there is actually a factor, okay? So if you apply 1.0, right? If you apply one, if you put in one there or just use yes, we're actually gonna limit that stabilization energy to 1 to the power minus 4 times the strain energy. So whatever strain energy is that is experiencing in the model, we are just gonna apply this factor here, okay? So if you put in any other value other than 1, it's gonna be how many times of this, okay? For example, if I apply 2.0, it's going to be 2 times of this 1e minus 4. Okay, so it's going to apply 2. You can apply up to 2e minus 4 for the particular problem, right? So that's how you can add or decrease the stabilization energy. Okay, why is this so small? Because this will actually affect the results. Okay, so this is additional energy that you apply to the model to stabilize it. And of course, with any additional energy, you're actually gonna influence the results. So that's why we don't put this to be too high. And it's always a factor of how many times the strain energy that's experiencing in the model, right? So yeah, you can use this, especially if your model is having a very hard time to converge. If your model is a buckling problem, then applying this static stabilized energy here will help you achieve convergence. Okay. The rest of the keywords I will touch on it on the next chapters. All right. Okay. Wait, let me just share again. My screen is cut. Right. Okay, so now let's talk about the output. As we know, we can output with the NL out. Okay, so that will output according to our time set that we want. These are the outputs that you can request. Normally your stress strain, all those are basic. SPC force are also requested. You can request for them. Yeah, basically those stress, strain, displacement, even contact force are available for output as well. So those are the basics. Now we have this implicit out here. So if you want to output results during runs, okay, so let's say if you're solving at 0.1, 0.2, 0.3, and you want to see the results of those time steps, even though the run is not completed yet, it's not reached 1.0, but you want to see and check a model whether it's realistic or not, whether there's any error or not. So you can actually request for this param implicit out. Okay, so this is param implicit out. This will allow you to this will call the Optistruct to write out solutions after you have solved, let's say, some particular time step. Okay. So even to look at what's happening during the run, or you just want to open your hyperview and then look at the results during the run, you need to request for this param implicit out. Okay. Otherwise, you only get the results only at the end of the run. Right. If you look at the out file, this you can look at the progress here. You can see what's how many iterations being solved for the particular increment. Okay, so you see some data load step. This is the load increment here. So now this is already solved. The load increment of 0.1 or 10%. You solved 10% of the run, and these are the convergence checks that it performed. Okay, so remember for displacement error, it has to be displacement and load error has to be lower than 1e minus 3, and for work error is to be lower than 1e minus 7. Okay, so you see that the first step, the first iteration, it didn't converge because here is high. Then on the second iteration, yes, converge. Right. So here is how you can look at the out file to understand better of where your run is experiencing problem at what load increment. Okay. Yep. So as I mentioned, NL out card controls the output for for your nonlinear analysis. Okay. So this NINT here is the number of intervals that you want to output. So by default it's 10. That means you output every 10. Let's say if your load full load is 1.0, right? So the time is 1.0. Then default 10 means you output every 10. Every 10%, right? But because of this being a non-linear run, we need to check for convergence. Sometimes it doesn't always output at 0.1, exactly 0.110%. Okay, if you set NINT equals to 10, it will also have, it will still have 10 outputs, right? But then you might not get specific at time equals to 0.1. You have one output, 0.2 you have one output. It might be 0.1. There's some small values at the back here, so it won't be exact 0.1. If you want it to be exact 0.1, the third card here, instead of NINT, you use a time. So I'll teach you later as well. You can use a time where you specify a set. All right, a set for the timing that you want the output. So for example, the set you will define 0.1, 0.2. So this will exactly output at this particular times here that you set. Okay. So I'll teach you later on how to do this as well. Yep. So this is what I mentioned. For NL out, you can either output in frequency. You can use frequency. So how frequent do you want? Or you can use time with set. Okay. So normally I'll use time with set so that I can output at particular times here. Right. Previously, this is new. Previously, we don't have this. So previously, we were just using the NINT, number of intervals to output. Okay, and we just determine how many intervals to output. We cannot exactly set what's the particular time to output, but now we can with the new version. All right. Okay, so best practice before you start running a nonlinear analysis, always make sure that there are no rigid body modes, so you can run with if you can run a model analysis, make sure to check your mode shapes, right? If there's any rigid body modes, or you can also run a linear analysis first to make sure that everything is properly attached, properly connected before you start running for a non-linear analysis. Okay, then you start simple, so means you start with linear first, make sure it's okay. Then you run with a non-linear. So non-linear, you add complexity one by one. So maybe you want to start with a non-linear material. Then you add non-linear. Okay, so the easiest is go to large. You first start your large displacement analysis. Then you put in your non-linear material, right? If that's also converged, then now you can consider non-linear context. Okay, so you add complexity bit by bit, so that you get to if there's any error, then you get to debug it easier. Okay, if there's any convergence issue, you can get to see it easier because you know what you have added to the original run, which is just a linear analysis. Okay. So the termination time is automatically controlled in nonlinear static analysis. It's always 1.0. Okay, so you use that. We advise you to use that because when we print out in the out file later on, you see that the load step is actually just a factor here. Okay, so if your termination time is not 1.0, then you cannot read this as 45% of the applied load. Okay, so for easier interpretation of the out file later on, we advise you not to change the termination time. It's actually already set to be 1.0 unless you purposely change that. Okay, so just use this first because it's easier to read when you read the out file later on. When you see here 0.45, you know that it's actually 45% of your applied load. Okay. Okay, so yeah, so use DT on error palm to achieve better convergence, especially in the first step. So you can also try this later on, right? So let me see the exercise here. I'll show you guys how I can run this. I won't use this one. I'll straight away use this buckling analysis because here I will need to use the stabilized card to stabilize this run because as you know, buckling is highly unstable. So I'll use this example, right? You can try what I've done with this setup with this model as well. Basically, it's the same, but here we have a bit of a challenge here with the convergence. So I'll demonstrate this, right? Right. So just want to explain first. So you see that here, in my slides, you see that there is one exercise page, and then there is these results already, right? And there are no steps in between. Okay, so if you want to look for the steps on how to set up, okay, you would have to look at the under the exercise models that I sent to you. There is one student manual here. Okay, so you go to that, and this will actually show you step by step. All right, so this is the step by step. Right, so if you look for steps, you go to this yeah, so this manual here. Okay, so this manual will actually tell you step by step. And the slides doesn't show you those step-by-step guide. Okay, so even look at step-by-step, make sure you go to the student manual here. All right. So let me just open the model now. Oops. Right, I'm going for stabilization. Okay, so this is just a normal dog bone. Okay, normal dot bone with SPC at one side, and then there is a SPCD and force displacement on the other side, right? So material properties are already set up, so I don't need to deal with that. All I need to do here is they already set up this for a static run. Okay, so no, not static run, but non-linear static. But they have also defined the NL palm card, which is needed, right? T load here is just the loading history for the enforced displacement. Okay, so it follows this loading curve here. You see that curve from this table, right? So it will follow this. The load will increase like this. Okay, this is the load increment. You can use this as well if you want. If your load is not constant, if your load is constant, then you don't need to do this. Okay, but if your load is not constant, means that for a particular time step you pull by a certain displacement here. Okay, but if your load is constant, then you don't need to do this. Okay. Table S1 here is for material. So they also have a non-linear material here. Okay, plastic region is defined with this table for tin, which is this one here. Okay, so this is the stress strain data for that material. Right. You see here you see that it actually starts from 300. Okay, so this curve, stress strain curve here, is not starting from the 0, 0. It's actually starting from the yield point. Okay, so this is just defining the plastic region. The linear region is still defined using the MET1. Okay, so the linear region of the elastic region of the material is still defined with this MET1 here. Only the plastic region is defined here with this MET-S1. So I'll talk more on this later on in the next chapter. Okay. So now this is a run that's already set up for nonlinear analysis. Okay, you see SPC is here. Excuse me. SPC is there, and now palm and then out. They're all properly defined already. Okay, so we can actually run that. Right. So let's me try to this one. Just make a copy so that I know overwrite the original. Okay. If you are using V2021, we no longer have Optistruct. All right, so V in 2020 you still find Optistruct. Okay, there's Optistruct here. Okay, but for 2021 you don't find Optistruct already. Okay, because we have converged all the solvers under compute console. Okay, so you need to search for compute console. This is the file. Make sure you turn your solver into Optistruct. So all these solvers has now been converged under this compute console here. Right. So make sure there's Optistruct, and I open that file. All right. So I'll just run that very quickly under class open. No, not too much. Okay. Okay. So yep, this will run, but this will actually have some error in convergence. You can look at the monitor file when it's running. Okay, so this will show you step by step as well. So now it's being updated, right? I normally look at the monitor file because it's easier to read comparing to the out file here. Okay, so if you look at the out file, sometimes it's a bit harder to read. I normally read the monitor file. Okay, So you see here, that this is the cutback. So every time it experience a convergence issue, it will cut back, and you'll now run with a smaller time step. So you see here, this is the time step that you first ran. This is increment 7. Okay. The time step here is, this is a time step. Okay. But it cannot converge, so it converges no. And then it now is forced to cut back. So there's a cutback 1. And for this cutback 1, it now ran with a smaller time step. So every time we experience a convergence issue, we will actually reduce the time step by 25%. Okay, so reduce the time step and then try to achieve convergence. So now this is achieve convergence. Okay, so it continues to increment number 8. You also achieve convergence, yes, but then at increment number 9, it experienced a convergence issue. So now it cuts back again. So now from 20.025 time step, it now reduced 25% to just 0.6. Okay. So it reduced the time step by a quarter and then try to achieve convergence. So now yes, yes, yes. So a few times with this small time step, yes, it has managed to achieve convergence. So now it tried to increase the time step, right? So it will actually increase by 50%. Every time it has successful convergence, you'll try to increase the time step by 50%. So now increase 50% here, and so this has also achieved convergence. Then you also increase again 50% the time step and try to run and achieve convergence as well, until it bumps to a no, cannot achieve convergence. Then it will reduce again back the time step. So this is a automatic time control that we actually adopt to make sure our run can solve faster. And if there's any error, it will cut back and try to solve with a smaller time step. Okay, so this is done automatically, right? So now you see all the while is pretty okay, except here it has cut back 4 times and then it has now failed. Okay, so you cannot achieve convergence for a few time step. You can see the time step has actually gone very small. Okay, 1e minus 9. So if you look at the out file, right, so you see that the error now, the maximum time increment has been reached because by default we only allow 5 cutbacks. Okay, so C1, 2, 3, 4. Yeah, it hasn't reached C5 yet, but then the time increment has been reached. So there's also a limit on how low you can go. Okay, so now it's actually reached that limit. Means that even though if I reduce the time step further, let's say if I reduce up to 1e minus 20, it still cannot converge because there's actually issue in the model rather than this being the real factor. Okay, even though we report that the error is due to the maximum time limit that's been reached, by right, if we just, let's say we reduce some more the time step, right, we might be able to achieve convergence, but then maybe for this increment, but not for the next increment, because there's definitely something wrong with the model. The model is unstable. Okay, so it doesn't always mean that you increase or reduce the time step here, you can achieve convergence. Okay, yeah, this I will have to admit that this error is a bit misleading. We just say this, which sometimes makes the user think that if I just increase the time increment or reduce the time increment, then my run can go through, right? But it's not usually, it doesn't always solve the problem there. Okay. So when you have this error, all right, when you have this error, what you can do is normally you will see that the error is being reported. You will see from the out file as well. Now this is correction number 5. Yeah, it's been correction number 5. Yeah, actually reached 5 cutbacks. Let me double check on the monitor file. It should also report 5. Okay, so yeah, something's weird. Let me check on that. But from the out file, from the out file, we know that now it has actually reached correction number 5, means there's 5 cutbacks, and it still cannot achieve convergence because you see here that the work, the convergence check for work, it has to be lower than 1e minus 7. Now it's 5e minus 7, so it's still higher than the tolerance. So that's why it has failed. Okay, so let's look at the model. Let's look at the model and see what's happening with the run. Okay. So far so good. Are you guys okay? If you have any questions, just type in the chat, or you can also unmute and ask me. All right, so if I look at the model now, H3D. Okay, so this is the model. It's non-convergence, and these are the steps that yes run a step here. Yes, produces non-convergence here. So if you notice from the model, you see that there's also NL out. Okay, so NL out, we set here the number of intervals to be 33. So every so every 0.03 it has an output. Okay, so because of the 33 intervals that we want, right? And then there's a non-convergence here. Since we have this save non-convergence, by default now it's turned on to be yes. Okay, so if you see it's no, but if you don't turn on this, it's in yes now. So we actually output the final step that is non-convergence as well. Okay, previously it was set to default no, means that you don't see this final step. It means you don't get to see this last step that is not convergence. But now we have actually set it to yes. Okay, so let's look at the results. All right. Let's see displacement for now. And let's look at the animation. Yeah, you don't get to see anything. Okay, there's you see this wrinkly here, this wrinkle of the material, right? So as I mentioned, buckling is highly unstable. So that's why now you see this. I'm not sure if it's visible to you guys. Yeah. If you cannot see from my model, then if you run this later on, you probably can see it. You see there's actually like something there's a zigzag of the dog bone here, right? Yeah, so because of this is actually, this is the last step where they experience that non-convergence. Okay, as I mentioned, buckling is unstable, so that's why you have this issue here, right? So this run is not stable. One way to counter this is to introduce the NL adapt. Okay, so we just need to create another card called NL adapt, right? So this introduce some solution that can actually help you achieve convergence. So you see here there are a few options. One is the number of cutbacks, and then DT max is the maximum time increment. DT min is the minimum time increment, right? So if you look at the error just now, he has just mentioned that in the out file, the error that is mentioned that the error mentioned why it failed is because the maximum number of time increment cutbacks has been reached. Means that it has now run to cutback number 5 and it still cannot converge, so that's why it failed. Okay, so you might think that, oh, because number of cutback is not enough, so I just increase my n cuts here. Why don't I just increase my number of cutbacks here to, instead of 5, I increase it up to 10 or maybe 100. Okay, but this will not actually solve the issue. Yes, you increase up to 100, you will just drag the running time. So you probably run correction number 100. You still cannot achieve convergence because the issue is not with this time increment here. The issue is really with this material. You see that this buckling here, because this buckling here is highly unstable, it causes this material to wrinkle like this. Okay. So increasing this to 100 will not solve the problem. Okay. Instead, you can actually try to introduce this stabilized energy. Okay. So let's just put in a stabilization energy of 1. 1 here, remember, is 1 times 1e minus 4 of the strain energy. Okay. So 1 times 1e minus 4 of the strain energy that is being experienced in the model at the current moment. Okay. So it's not exactly applying 1, right? We'll just introduce a bit of stabilization energy here to the run and make sure, and let's see whether now you can converge or not. Right. So just output this again. Before that, you set the cut here and then adapt. You need to apply it on the subcase as well. So under the subcase, make sure you apply the annual adapt also. All right. Then I can output this. And let's just rename it. Annual adapt. Let me just rename it as stabilize here. So remember the stabilize that we introduced, the energy is 1.0, right? 1.0 times the 1e minus 4. So 1.0, save, and let's run that now.
Raymond, how do you input NL adapt?
You first
you right click at the load collector.
Yeah, load collector, you right click, you create a NL adapt.
Okay.
Then you put it under the subcase. Okay, so I run this stabilize 1.0 now. Okay, and let's see now whether it will achieve convergence or not. All right.
How come my one, when I point to create, it doesn't list out the thing?
Are you using
2020?
Optistruct?
Yeah.
You're using solver interface Optistruct?
Yeah, our Optistruct.
When you right click on load collector, it didn't come out this list?
Yeah, I did. Yeah, I go to create, but it doesn't come up the list.
Okay, because you're using older version, just click create first, and then
Okay.
later from the cut image you can change to another.
Oh, okay.
Yeah. All right, so see if this will converge now. My guess is it won't. Actually pretty good. Yeah, I think all converge. Okay. And it's completed. It ran all the way up to 1.0. Okay. So let's see whether this is now converge or not. All right. So I will open the one with a stabilized energy. All right. So even though it has converged, I still see this wrinkle here. Okay. Wrinkle here. All right. So comparing to my results that I'm supposed to get, it's supposed to wrinkle like this. Okay. So as I mentioned, buckling is highly unstable. Right. What you see now is actually a buckling. Right. You see this is actually a different mode shape. So buckling also has mode shapes, right? And this is one of the modes, definitely not the modes that we want to predict. So if let's say if you're doing testing and you find that your buckling actually happens like this, it doesn't happen with this W shape here, then your models, your run here is actually not capturing that actual behavior, right? So even though it's converged for me, but the result is not what I want. That means the stabilized energy is actually not enough to stabilize the model yet. Okay. Yeah. So let's try to run. Now I will increase my stabilized energy. Instead of 1.0, let me increase to 2.0 now. Okay. So I increase to 2.0. I don't need to go to my HyperWorks. I can actually edit from here. Just look for the card and you see stabilize 1.0 here, increase it up to 2.0. All right. So that's the benefit of using input DAX. You can easily go to your card and then just increase 2.0. Right. And now let's just try to run again with 2.0. Okay, so now this is stabilized energy 2.0 and run this. Okay. All right. Probably gonna run this faster next time. So in case 2.0 doesn't give me the results, I will then increase my stabilized energy. All right. So it's done. Let's look at the results now. Let's do 4 times. I open another one. 2.0, open line. So now this, I think this is better now, right? So this is now capturing the results that I'm supposed to get. Just do 3 string. Okay. So you can see from the initial run where there's no stabilized energy, cannot converge. Here we increase a stabilized energy, and you see there's a different kind of buckling. Buckling is highly unstable. You can go to any of the modes, right? Now this is the mode. This is not the mode that we want. So we increase the stabilization energy again, and we achieve this now. So this is probably the results that we get. That is gonna be similar to the actual case, right? Okay. So if you are dealing with highly unstable problems like buckling, then turning on this turning on the stabilization energy will help you achieve not only convergence but also achieve correct results. Okay. So the next question is, with all this energy that I introduced to the model, how do I know what is my limit? I can increase 1. I can put my stabilization energy to be 1, to be 2, to be 20 to be 100, right? So what is my actually limit to know whether enough is enough? So one way to check is to look at the energy here. So for all the energy that you apply to the model, we actually write out a E dot NLM. So this is the energy that we apply, or this is like the energy check that we check on the entire model. Okay, so if you look at, if you just double click on this energy session file, energy MVW, this will open hypergraph, and you can actually look at the basically it's just this file. This is just a text file of the energy that is experiencing in the model, right? And this is harder to be looked at, so let's just use the session file. Double click on the session file, energy.mvw, and it will open in hypergraph. Okay, so this is the strain energy that's in the model. All right, this strain energy is pretty high because this is a buckling problem, but you can see that the static stabilized energy that we apply, this is the static stabilized energy. You can see that's actually pretty low, okay, because of the limit that we set. And for a general rule, how much you can apply, as long as your static stabilized energy is less than 10% of your stabilized energy, then your model is still accurate. Okay, so you can see that the strain energy that is at the end is about how much? 574, 57.4 K. Okay, and you can see that the stabilized energy that we introduced at the end is actually very low, right? Definitely less than 5%. Yeah, less than 5% actually. So as long as your static stabilized energy that you introduce is less than 10% of the strain energy, then your model is fine. Okay, so there's one rule or one guideline you can use to determine how much strain energy you can introduce to your model. How much static stabilized energy they can introduce to your model. Right. Okay. Any questions? So again, you can try to run this as well. This is fairly simple. Just create an adapt card and then use the static stabilize to introduce stabilization energy to your model to achieve convergence. Okay. So the final result we should get is something like this. It's not a wrinkle like this. Okay, it shouldn't be wrinkle like this. All right. Some of you might get a buckling that is buckling on top. Okay, so I've seen before some in previous classes, some of the results is still buckles like this. You still get a V shape, but instead of V shape in the bottom part, you V shape upwards. Okay, so that is also possible buckling solution. As I mentioned, buckling is highly unstable. It can go positive, it can go negative, right? So if it's still V-shaped but in the opposite direction, that means it's upwards, then it's still okay, right? Because buckling, this is a symmetry model. Buckle can happen both ways, either up or down. Okay, there's no rule saying that buckling will always happen at the bottom here, because this is a symmetrical model, right? So yep, it's highly possible that you can also achieve a solution that is buckling upwards, right? Nonlinear materials. So for nonlinear materials, I think it's pretty clear where we actually need to use it, right? When your material is behaving in the plastic region, or you expect deformation in the plastic region, okay, then you definitely need to use nonlinear materials. Okay, so here's a list of the material cards that we have. Non-linear materials is actually elastoplastic, especially is under here, Mat S1. And we will also be talking about MetHE. So if you're dealing with hyperelastic materials, rubbers, then definitely need to use MetHE here. Okay. Okay, so Okay, so I don't need to go through this theory here, when it's plastic, when it's plastic. I guess you guys are pretty familiar. And also the equation here. Let me see. Okay, so let me just explain a bit on this, because this has to deal with when we define the cards for the Mat S1. Okay, so for Mat S1, we actually have the option. Later on, you see that we have the option to define our curve, whether it's using total strain or using the plastic strain. So the example that we saw earlier is actually defining the curve in the plastic region. Okay, but there's option to define your full stress strain curve also. Okay, so that's the total strain. So just need to be aware of that when we apply, when we set up our material later on. Okay. Large strain is available in Optistruct by default, so there's no need to turn them on. Okay. Large strain when your plastic strain has achieved 5 to 10% plastic region, right? So then you need to actually turn on the large plastic strain. But we already have it in our elements by default, so you don't need to turn it on purposely. Okay. Theory part, I won't go too deep on this. You guys are familiar. Right. So this is just to explain the large strain and so small strain. Okay. Consider this model here where we apply the load, and then the second load case we remove the load and then it springs back to the original position, right? So when it's loaded and unloaded, if you're using the small strain formulation, you see something like this. But if we use the large strain, this is again by default already on. You don't need to turn this. Okay, so you see that our solution will be more accurate in capturing the large strain displacement here. Okay, so yeah, this is to show you that there's a difference when we use small strain versus large strain formulation. But rest assured that we already consider this already. Okay, so this is automatically turned on in Optistruct when it's needed. You don't need to purposely set up any cards for that, right? Strain hardening, we have a few strain hardening available in our material card. You can see that you can choose any of that from our defaults. Okay, so by default, there's going to be isotropic hardening, but if you have a different hardening, then you can also use it. This is only used if you do not have the stress strain curve. If you already have the stress strain curve, then you don't need to define the hardening model to be used. Otherwise, you can use any of the hardening models here to specify your material. Okay, if you don't have the stress strain curve to define this region here, then you can use any of this. Right. Yep. So that's the hardening rule and also the hardening slope. So that defines the plastic region. But if you already have the stress strain curve, then you actually don't need both of these. Okay, you directly just put in your table here, TID. Okay, so directly put your table here for the stress strain curve. Let me see what else. Yeah, I think I'll walk you through from the HyperWorks GUI later on. Okay, but remember we are using this Mat S1. This John Cook here is similar to the John Cook in Radios, right? So yeah, this is new. If you're using let's say John Cook in Radios, you want to use it here as well, you can use this card to set up. Okay, it's basically just an option to turn on under the Mat S1. Right. Right. So there are a few hardening rules that we can set for the plastic region here. Okay. And then we also need to define the slope. So this is a slope for that. H value here. Let me turn on this. So the H value here defines this slope here. Okay. So we will require that if you do not have the table. If you don't have table, we require the slope and also the hardening rule to use. Okay, limit 1 here is the yield stress. So basically, this is the point that you need to put it under limit 1. Okay, so yep, it's clear. Otherwise, you will just use a TID, table ID, to define the stress strain curve. Okay, for stress strain curve, again, you need to define what's your data type. Is it a total strain or is it a plastic strain? Total strain means that your X means your stress strain they define in the table. XY has to be 0, 0. Okay. Of course, for plastic strain, it starts from the yield point. So yield point, your stress will have certain values. Your strain might be 0. Okay, but your yield point may be your yield stress. Okay, so Y is this is the first point of your stress strain data. Okay, so if you're using total strain, make sure your data here is 0, 0. If you're using plastic strain, make sure data here has some value for the stress. Right. Yeah, so basically this is it. I can't remember what is being used in radios. Is I think by default is the total, if I'm not mistaken. Okay, so if you directly convert radios material into, let's say your radios, your stress strain data in radios, you have to convert it into Optistruct. You just make sure whether you're using total strain or plastic strain. You just define it under the type strain here. Okay, type strain needs to be either 0 or 1. By default is 0. By default it's total strain, so your stress strain data is to start from 0, 0. Okay. If it's not, then you need to define it. Your type strain here equals to 1, and then your stress strain data will start from your yield stress. Okay. Right. So this is the table that's going to define your stress strain data. Table S1. Okay. You see here there's an option for flat. Okay, so flat equals to 0, flat equals to 1. Basically here, because your stress strain might just capture up to a certain point, if your strain exceeds that strain data that you have in your curve, let's say this is your curve and you only have strain up to, let's say, strain n here. Okay. Sorry. Strain. Okay. So let's say you have only data up to strain n, but now your strain has exceeded. Now you have exceeded strain n plus 1. Okay. But there's no data for strain n plus 1. So if you are using flat, okay, so flat here means that this will just flatten the curve. So after, I mean, a good example for this. Let me just redraw here like this. Okay, so I say now this is strain n. Now you're required to find what's the stress level when strain is exceeded, has exceeded your data in your curve. Okay, so if you put flat equals to 1, that means after this point we'll just flatten the curve here, and probably we get this. This is actually strain n plus 1. Okay, but if you use the default, which is flat equals to 0, we're actually going to extrapolate this curve. Okay, so then your stress reported will be higher, right? So stress reported will be higher if you use flat equals to 0, higher or lower. Okay, so because it's extrapolation, right? But if you're using flat equals to 1, then it's just going to be the same as when your strain is equals to this maximum strain here. Okay, so just take note of that. What kind of data that you will get if your strain exceeded if the strain in the model is exceeding the strain in your material data, right? Okay, so we support both small and large displacement with the MET S1. Okay, so it doesn't always have to be large displacement, only can use MET S1. Even small displacement you can use MET S1. right? What else is important here? Let me see. Of course, if you need large displacement, you need to turn on param large displacement here. We'll see this later on in the nonlinear geometry as well. There are two ways to turn on. One is either use the NL palm bracket large displacement or set a param here. So let me just quickly show you from here. Here there's a NL palm card that's being set up. If you want to use it with large displacement, you can define it under here. Okay, so this is the subcase. Under subcase, if you define your NL palm, instead of putting it here, oops, let me just. So instead of putting it in NL palm here, I put it under the NL palm bracket large displacement. So this will turn on large displacement also, right? So if you put my NL palm card under here, this will turn on my large displacement, right? The other way to turn on large displacement is to set up a param card. So let me see, param. Yeah, so the other way is to set up from here. Param, large displacement, you just turn it on to 1. Okay, so this will also turn on large displacement. Right, so in this model here earlier, it was set up here has a large displacement equals to 1. So that's why here in the step here, we define it as NL palm under the normal NL palm here. Okay, you didn't use this NL palm bracket large displacement. Okay, so two ways to turn on large displacement. Right. Always turn on. Right. This large strain solution is always turned on when our plastic strain exceeds the small strain deformation theory. So when the strain that is plastic strain in your model is exceeding 5 to 10%, then we will turn on large strain solution automatically. Okay, so don't worry about that, right? When we report the results, plasticity results, you can actually get all these strain here. You can get total strain, plastic strain, and also elastic strain, right? So you can look from just from the hyperview drop down. You can choose the strain that you want to look at later on. Okay. We will also report this equivalent plastic strain. Okay, so yeah, just take note that equivalent plastic strain is calculated using this formulation here. Okay, so normally especially those abacus users, right? They will normally use equivalent plastic strain. So that's why we have this result here that is also printed out if they want to do a comparison or if they're doing any benchmarking with abacus results. So that's it's calculated at integration point and then average over the volume, the entire element volume. So some of them use this to look at the plastic strain results rather than looking at this total strain here. Okay, so yeah, you can look at both and see which one is more accurate comparing to your testing. Okay. Here are some strain results that we can actually output not just at the corner, but we can also output at integration points. So by default, it's going to output at the element, right? But if you want corner results, if you want integration point results, then you can turn on these specific cards here. Okay. One general question is, should I always use the true stress strain curve or engineering stress strain curve when I put in my stress strain curve for my Mat S1, right? Where small deformations are concerned, there's actually no difference, not much difference. Okay, but for large plastic strain, then it's better to use the true stress strain curve. Okay, so true stress strain curve is better when you are dealing with large displacement. So in general rule, just use the true stress strain curve, okay, and put it in the mat S1, right? So that's the if all these words here, the rule that I need to remember is just this one: use the true stress strain curve, right? When you're defining the table for mat S1, okay. So here we have a small exercise to compare small strain and also large strain, right? Of course, if you run with small strain, it definitely won't capture the curve behavior correctly. So the steps are the same. I'll just demonstrate how to set up, especially mat S1, in using this exercise 2B, which is actually for large strain, right? So you will see that we will actually import a material table inside into HyperWorks to generate or to create that S1 card, okay, and yeah, then set up the rest for the analysis, okay. So this is what we should get. The blue curve that you see is actually from a material testing data, right? So that's the raw data, and then the red curve is what we get from Optistruct. Okay, so we're trying to match the testing material. Okay, so just bear with me a few minutes while I set this up. I know it's close to 12, but I hope you guys can just spare a few minutes to look at this setup here. Right. So I will load the model in. Large strain, okay. Okay. So let's see, the material is there's only mat 1, right? There's no non-linear material yet, so we need to set up for that. Property wise, SP last, but there's no property for this main material as well. Okay, so we need to create a P solid for that, and then define the material there. Okay, so let's just do that first. Let's just create a P solid. P solid, all right. P solid. Material wise, I can just assign it first to use this one. Okay, because mat S1 is actually defined underneath. All right, so let me check on the sub case. Oops, there's no sub case here as well. Let me. Oh, we need to create the boundary conditions. Okay. All right, so for boundary conditions, I'll just refer back to the manual so that I will get the same result that is being presented in the slides. So let me just go back to the manual. You can also open up the manual. And then follow the steps in the manual. So I'll just go to 2B. Let me see where are the loads to apply. Let me see. Okay, I have my rigids already. Okay. Right, so this is where I'm going to pull it. The other side is where I'm going to clamp it. Okay. Right, so let me just clamp this part first. So when I clamp this, I'm not going to clamp the entire thing. I'll just let me hide some of these elements first. All right. So I will create a SPC. All right, so just the top and bottom layer and just log 1, 2, 3. All right. Okay, so that's the SPC. Make sure it says just created that. Okay, I'll rename this to SPC. All right. And on the other end, here's where I'm going to apply my loading. Okay, so I'm going to apply my loading in the middle here, which will also require an SPC. Okay, if I'm using a SPCD, I need to define a SPC at the point of location, at the point of application. So I'm going to apply the SPCD here, which is the enforced displacement. So I need to define an SPC there as well, right? So SPC, yep, create that. So this one SPC, and I would now create. I will just ungroup this. Create another card. Okay, so just a dummy card first. And then change my card image later to SPCD. Oh, sorry, SPC ungroup, right? So then I create another constraint, which is called SPCD type now. And I'm going to pull in the X direction. Okay, X direction. Let me see how much. 20. Okay, so it's going to be put in the X direction for 20 mm. So just bring 20 here, click on the point. Whoops. Let me create again, click on the point and create. Okay. So now this is the SPCD. Enforced displacement on this point is going to pull in the X direction for 20 mm. Then there's a SPCD for the clamping side, and SPCD, the enforced displacement need to sit on the SPC also. So that's why we define the SPC here as well. Okay. Right. So that's that. Loading is there. Any question on loading? Test attention test. Hobby is there. Right. So for the material side, now let's create that mat S1. Just need to check on this. We're using table, so we need to read in a curve first. Okay. So for the easiest way to read in is to use the utility tab, and you look at this table create here. Okay, so just click on that table create, and we're going to import a table in from the CSV file, and we're going to create a table S1. Right, but before that, let me just look at the table first, see what type it is. Okay. Plus 50, right? So this is table we're going to read in. It's actually starting from 306, right? So it's plastic strain. It doesn't start from the total strain. So plastic strain curve, and I'll read this in. So just from the table here, import table, table S1 X, then we put in the file here, right? So let's just search for the file. CSV. Okay, this is the plasticity. Create a new table. Just call this stress strain. Okay, apply. So it's created. You see it under the curve here. Okay. So you see this is the stress strain curve that we have read in. Okay. So yield is 306. We can update that in our mat S1 here. Okay. So just check mat S1 to enable it. Table TID will be using this stress strain curve. Right. Type just leave as by default it's going to be NLE last, so you don't need to do this one. Okay, so by default, yeah, default is plastic, which is elasto plastic material. So we're just going to use the plastic here. Okay. H is the hardening hardening slope, so we don't need this, right? Because we already defined the stress strain curve. Even the U function we don't need. Hardening type we also don't need. We can put in our this is limit one, which is the U stress, which was 306, and type strain because we are using the plastic stress strain, so we need to define it here as one. It's not the total. Okay. What if you put it here as 0, or you didn't define this as 1? By default is 0. Okay. But if you put in a stress strain curve that is not 0, 0, here is 0. The first point is 0 and then 306, right? 0 and then 306. If you put it as 0, you will inform an error. Okay, so it will output an error. So yeah, make sure it's 1. And basically that's it. So you have set up the non-linear material. Okay. Remember, just use the utility table create to read in your stress strain curve and then define it under mat S1 here. All right. So, all right. So this one is done. Set grid measure. You see where's this grid here. Solid. Okay. All right. So let me renumber this first. So that I know which point to output the results later on, or look at the results later on. Okay, so I renumbered the node here to 11. All right. So there's node 11, which I'm going to look for the results later on. Okay, just make sure our outputs are done. Let me just do a global output request. Okay. Since I'm gonna track the force versus displacement, I will need displacement. I will need force. So force here is actually the reaction force, which is actually the SPCF here. Okay. Yep. Because there are a lot of SPC, So maybe I just want to output for let me create that set first. I'm just going to put that grid number 11 there so that I need output for that because there are a lot of SPC. Later on, I need to search for the SPC. So I'm just going to look at the reaction force of here when I've pulled this one. Okay. Think we okay, never mind. I have to skip this. We just look at all of them. Later I know that if I need, I just go to N11. And yeah, basically that's it. So make sure the SPC force is output for all. Displacement is output for all. You even look at stress and strain as well. Stress is by default on, but you can just turn on here, stress and strain. And yeah, I guess that's all. So those are the outputs that we need. Double check on the subcase. It's not created yet, so we need a subcase. Create load step. Right, so just rename this first. Change this to NL stat, non-linear static. SPC is already there. Okay. Load is your SPCD. Okay. Oh, we need NL pump, so create a NL pump card for all non-linear. We need NL pump. Okay. Initial time set, let's just do 0.1, so you can go up to 10% in the first step. Next, we would need NL out as well. Oops, NL out. Okay. This is to govern the output. So let's just do number of time increment. Let's just say 10. In terms of if there's any non-convergence, it will output that step as well. All right. And now adapt is optional. I probably don't need any static stabilize here. What else do I need? I think that's all. So put in your NL pump. This is large displacement. So if you do not want to create a param large displacement, you can directly use this NL pump large displacement here. Okay. So just do NL pump and then NL out. Okay. I also like to use a monitor to monitor my run. So if you look at the monitor file, let me see if I can pull up a monitor file. Right. So previously, like all this monitor file here, it will actually monitor a grid. Okay, you see the grids here are pretty random. If you want to just track a particular grid, you can specify the grid here. Okay, so it's using this monitor. If you scroll down under your subcase, there's this monitor here. Just turn it on, and you can specify which grid to look at. So I'll just look at grid 11 because this is the grid that is being pulled, right? So I'll just look at grid 11. How you progress over the entire simulation. Okay, so I'm just going to track direction 1, which is the X direction, right? So that is more for monitoring purposes. It wouldn't affect the run. Okay, so large displacement, yep, that's all. So I'll just output now. Double check on my material. Yeah, so I need to define it as P solid. Material mat1. Okay, even though it's called mat1, let me just rename this. It's a bit confusing. So I just call steel. This steel is actually mat1, but it also has the mat s1 defined as well. Okay. Right, so let's output this one. Mhm. I should save it under here. Yeah. Okay. Of course, you can also run directly from here, no problem. Right, but I prefer always to output because I can double check when I look at this. Okay, so just double check. Here we have the nonlinear stat on, monitor is on, SPC load, right? So that's good. Now we can run this file. Any question on the setup? If you're lost, you can look through this video again, or you can also follow the steps in the manual. Okay. Load 2. Oh wait, I haven't defined load 2 yet. Where's my load step? SPCD. Okay, I created the SPC card, so let me just isolate. Somehow it didn't update that, so I'll make sure this is SPCD. Okay, update load type to SPCD. Right, so important that your load is always SPCD. Right. Okay, now I can output. Actually, let me just output this. I can actually change from the input deck itself, but since I've done here, I'll just output here. Yeah, on the last train, this is the file, save. Okay, export. So I'll just close this and close this. Let me rerun it. Okay. So you can follow the steps here. Of course, my step will be different because I might jump here and there. But if you follow the steps here, you also get to set up your run. They requested for element force because they're extracting the element force of the spring. Okay, I'll just directly use the SPC force to plot. Right. So when I plot this, okay, later when you see the plot, we have some test results here. You see that there's this test result.csv. This is actually not scaled up to what we are to the units that we're using in our FEA run. Okay, so that's why we need to scale this up and also move the both scale up both the x and y to actually get a match with our simulation results. Okay, because it's not scale up yet. So let's go back. It's still running. Okay, done. Okay, so it's converged. There's no error to that. All right, all the way up to 1.0. So let's look at the results now to compare. I would first open the animation. Okay, H3D, open. All right, so if you look at stress strain, this is the result. Okay. Okay, it's just a simple tension test. Now let's look at the material comparison. Okay, so I'll just open hypergraph and then load in my model. Okay, change this to hypergraph. Right, so first load in my results from H3D. Y-axis is going to be the force, so I'll just use the SPC force of node 11. Let's just use magnitude, or you can use X, but I'll use magnitude so that I don't need to use any absolute values later on. Okay, so X direction will be the displacement. I'll say node 11 as well in magnitude as well. So I plot this. So this is my stress strain curve. Sorry, my force versus displacement curve. Right. And let me load in now the result from the tests. Okay, there's test result. There's only column 1 and 2. So 2 is your force, 1 is the displacement. So here is column 1. Okay, column 1, basically your CSV score is just like this. Okay, so there's just column 1 and column 2. Okay, so yep. Column 1 is displacement, y-axis is column 2, which is the force. Okay, plot that. You won't see anything because the scale is not set correctly. Okay, so just use the move button here. Make sure your second curve is being offset correctly. So scale up to 2, and Y scale is it's basically just units conversion. So just refer to the values that's set here. You can scale it up. Let me see. To 1000. Okay, so that is the rate curve is the test results. Okay, force versus displacement of the test results. The blue one is from our simulation, right? So you can see that you might think that, oh, it's not actually, it doesn't match very well. Okay, not really, because we only output 10 results. So if we look at here, the time step that we have, you can see that we only have 10 results here. So if you were to increase the outputs for the simulation, you might get a closer match. Okay, so now we only at a few juncture of the curve. So if you want to examine this better, instead of just requesting for 10 outputs in the NL out here, right? NL out, NL out here, you need to request for more outputs. So 100, for example. So I guess in the manual, request for 20. I think it's also not enough. You probably need to request for 100 outputs. Then you only get a better match. Okay. So for me now 10. 10 outputs, I only get this, right? In the exercise here, it requested for 20 outputs, so you get a closer match. If you output for 100 outputs, then you get a even better match with the test results. right? So yeah, so basically here, this exercise will show you how to output or how to set up a nonlinear material using Mat S1, and then how you can look at the force versus displacement comparison between the simulation and also with testing, right? Hyperelastic material. Okay. So when you're talking about hyperelastic material, you have to deal with large strain, right? So with large strain comes large displacement. So definitely you need to turn on large displacement for this one, or this simulation here, okay? So yeah, needless to explain what is hyperelastic. I guess you guys are clear. It's normally those rubbers and then some of the foams, right? So we have these hyperelastic material models available in Optistruct, okay? And basically, what we're using actually is basically even if you have the test results, okay, for the tension, compression, and then for shear, we will actually convert those test results, those empirical data, to derive constants for all these material models here, right? So depending, you will choose which material model to use, and then we will use your input data, your stress strain curve, to create the constants for these particular models here. Okay, so depending on which one you choose, we'll develop those models. So it's basically a curve fitting to derive those constants, right? Assumptions for hyperelastic material, we are assuming a response in isotropic material, okay? It's a fully reversible deformation, and it's also fully incompressible or nearly incompressible. So keyword here is reversible and incompressible. Okay, so the volume does not change except for thermal expansion. Okay, so if you have any large deformation, it doesn't really change the volume of the material. Okay, right. So these are some of the models that we have in Optistruct implicit. And then for explicit, of course, we have that foam. Okay, so foam is not available in implicit. It's only available for explicit case, right? And we're using the MAT-HE card here. You might ask which material model is the best to use. So we are actually curve fitting following your test data, right? So if you have input, if you have test data input, but it's only available in the uniaxial direction, means it's just tension or compression, then Aroda-Boy's model is going to give you a good curve fitting, okay? And it's also good for higher strains. You can see here, this is the test data. The star here is the test data, okay? And you see Aroda-Boy's is this dotted pink line here. We managed to capture that pretty good, okay? And for if you're using the other models like Neo-Hooken and also Muni-Rivlin, you can see that it really didn't capture this second stiffening here, okay, for higher strain here. So yeah, if you only have uniaxial data, then probably Aroda-Boy's is the best, okay. Yo here is behaving similar to Aroda-Boy's, okay, but there this brown curve here, right? Right, so these are the formulations, don't have to worry about it. These are the 3 tests that you need to perform. Let me just share my screen again. My screen is cut. Okay. Right, so these are the 3 tests that you need to perform to capture that stress strain data and then put it into the MAT-HE for curve fitting, right? So you have the uniaxial test, your biaxial test, and then your planar test, right? And once you have that test, it's actually put inside his table 1, table 2, and table 4 here. Okay, this is for uniaxial, this is for biaxial, and this is for the planar test. Okay, and then if you know the constants, of course you put in the constants. Otherwise, using the tree table that you have put in, we actually curve fit and derive all these constants. Okay, so we choose your model here, which model to use, and then of course the Poisson ratio and also density, and then you put in your table data, right? Okay, yeah, the table data is important. And yeah, all these constants here are normally derived based on your table data. If you don't have, then if you don't have the curve data, then you definitely need to provide the constants. All right. Yeah, so example of the three test data that we have, and this is plotted using the Muni. Okay, so using the Muni-Rivlin model, these are the data that you provide, and then this is the curve fitting that we have done. Okay, so the blue one is the stress strain data that we provided. Then the orange one is actually the curve fitting. Okay, and in each, if MAT-HE is present in your model, we will actually perform this hyperelastic material constants. We will actually plot this out. We will show you what are the constants that is going to be used to represent your material model, your hyperelastic material. Okay, so yeah, all these constants are printed in the out file, right? And because hyperelastic is a large displacement, so we need to turn on. Always remember to turn on your large displacement, whether through the param or whether through the NL pump, right? So we need to turn on large displacement there. Yeah, tips on large displacement. All these are actually supported for large. Sorry, these are supported, but this one it can exist in the model. It won't fail if you turn on large displacement. But then all these elements here are going to be solved with the small displacement formulation. Okay, so we don't really consider large displacement for all these elements here, but all these here are supported, right? Yeah, so this is how do we get accurate model? If let's say you want to perform a curve fitting test, right? To make sure that Optistruct can get the accurate or can model can derive the constants according to your curve data. So you might want to perform with just one element, right? And then perform that, put in your curve and then get the output, right? Yeah, so always use first order to test. And if you have limited test data, right, means that you only have the uniaxial test, you don't have the biaxial test, you don't have the planar test, then some models like the fully polynomial and also the Ogden are going to give you bad. It's gonna give you bad curve fitting, so you don't actually get to derive the constants well enough. Okay. So yeah, probably it's better to use reduced polynomial like the Arada-Boys, the Yo, right, to get better curve fit to your curve data, especially if you only have the uniaxial test. So most of the time, what I've seen is that people only have the compression and tension compression data. They don't have the other test data. So it's definitely better to use the Yo Arada-Boys, those reduced polynomial instead of use the full polynomial. Okay. And if you're dealing with large strain, Ogden is accurate and can capture stiffening, right? But of course, also again, it's not meant to be used if limited data is available. Okay, so we cannot properly curve fit that material model, right? So this is an exercise where actually we already give you the constants in this exercise here. So what you need to do is just put in your constants. So if you refer to the manual, you see that we actually provide you the constants already. Let me see, where is it? Yeah, here. Yeah, so you actually we for this one is Mooney, so we just need to define all these constants here. We give you an example of the constants lah. But if let's say you don't have this, then you need to put in table 1, 2, 3. Okay, so the 3 tables refer to the uniaxial, biaxial, and also for the planar test. Right. So let me just show you how to set up. Again, this is also just a non-linear setup, so it's pretty easy to do. Just do new. Let me just read in the file first. Is it a HM file or a FEM file? Okay. Yep. So just read this in. I think everything here is set up. Let's just double check. Loads are here. We don't have load step yet. Load collectors only have the load and the force. So we don't have load step and also the other parameters, the NL parm and so on. Material is defined, but it's defined still for this part. The rubber actually is not defined yet. P solid is a steel material. This is only for this, not for this. Okay, so first off, let's define the material first. So you can just right-click, create mat HE. If you're using older version, then just create any material and then change the cut image here to mat HE. Okay, so I just want to call it rubber. So you choose which model to use. For this example, I'm going to use Mooney. Right, you can use here. It doesn't matter because we already have the constants for Mooney, so it's not curve fitting. So we don't need to, we don't need to, like, there's a limitation of which curve fitting is better for if which data you have, right? So here we don't have to worry about that because we already have the constants. Okay, so no curve fitting is done here. So put in Mooney. Let me see what's the value to use. Okay, so Poisson ratio, of course, this is gonna be high because this is rubber. So you can put 0.495. If you put it higher than 0.495, we will give you an error. You cannot put in more than, you cannot put 0.5. Okay, even though if that's the exactly Poisson ratio, but you have to put it lower. So 0.495 is fine. Some cases you can go higher, like 0.497 and so on. Okay, so I'll go with 0.495. That's the Poisson ratio. And then the constant that we're going to use. Okay. 0.12. All right. So if you do not have the constants, then you definitely need to put in your tables. So you need to read in 3 tables. One for the uniaxial data, your tension compression, the other is biaxial, and then the fourth one is the planar. Okay, so you have to, like what we've done earlier, input in the table create, right, using table S1, input 3 curves in, and then define them table 1, table 2, table 4, right? So with this one, it's actually okay. This is already set up for this material here. Now we just need to define a P solid for the rubber properties, right? So you see, this is the seal. It's not defined any material, any properties yet. So I'll just go down to properties, create P solid. Now you see there's a PL solid and then there's a P solid. For rubber, you can use both. Okay, what the difference is, For PL solid, it is specific for rubber material only, hyperelastic materials only, and it doesn't have the coordinate system. So the coordinate system is always fixed at the globe using the global coordinate system rather than a local coordinate system. So that's the only difference. If you look at the difference between them, the cards, here we can define this local coordinate for P solid, but for PL solid we cannot define that, right? So it's always going to use that global. Yeah, it's always going to calculate the stresses based on the global or the basic coordinate system. So we cannot define cot M for hyperelastic materials. Okay, so that's the only difference. The PL solid just simplifies that, right? It removes that. So you can use either one. You can use a P solid or you can use a PL solid. Okay, so I'm going to use P solid here. If you want to change it, just change this to PL solid if you want. All right. Then you can also put in your materials, which is going to be the mat HE, and that's it. Okay, so you see the difference between PL solid and P solid. You have more options to, yeah, create all this. Okay, but it's not available for mat HE anyway. So if you use either one, it's fine. Okay. Now we can need to define this for the component. Seal, we'll use that rubber property. Okay, and it's going to use that rubber material, which is the Mooney material model that we've defined here. All right. So the force SPC is already defined. All we need next is to, of course, create those cards for NL pump. So this is a good exercise for you to always create that so that you memorize it. We need the NL pump. Okay, that is always needed. What is the initial time step? Then we also need the NL out. Not need, but it's good to have it because it will organize the way we output later on, right? So how many output do we need? For this, let me just show you if I use time. Okay, I need to create a set. Okay, so I can say create a set here, and this is the set. I'll just rename this to time set, and then I put my values here. So how many outputs do I want? Let's say I'll output 10 at 10 time steps. So here I'll output 0.1, 0.2, right? 0.3, 0.4, 0.5, 0.6, 7, 0.8, 0.9, and then the last time step, right? So if you define it this way, you force the simulation to be done, to be carried out at this particular time, and then output at this particular time or load increment. If you don't do this, then you see previously in our examples, you see that our time step may not properly capture exactly at each 0.1 interval. Okay, you see there's a variation there. Okay, yeah. So if you just use the NL out and you set the NL out to be number of intervals and you set 10 intervals, you might probably get something like this. Okay, it's not exactly at particular that particular time. Okay, so to control that, you can use this one here. Okay, this set here, this set, and yep. So it's done. Now we are going to output. Oops. Let's go back to here. Our NL out is going to output at time. At what time? Based on this set time here. So the set time is created under the sets. Yeah, this time set here, which we have created earlier. So it's going to output exactly at these times here. Okay. So now out is done. Now I can create the rest NL adapt. Okay. And then if you want, otherwise I'll just go straight to it, straight to creating that load step. Okay. So yeah, so load step 1. Just change this to NL stat. nonlinear static, put in my SPC constraint. Okay, load. I'm gonna choose this force here. Hopefully I'm doing this according to the manual because I didn't look at it. Let's just double check. Where is it? Where is it? Okay, they're using SPC add. Okay, they have two steps. One is loading and the other one is unloading, and they're using SPC add. Okay, so let's just follow that. Instead of using the constraints, they're using this SPC add here. Which I don't have. Wait, let me just double check. Scale load is just scaled up to 3 times. So yeah. Okay, no worries then. I think this is a different model. So we just put in, I'll call this loading. And I'll put in SPC constraints, my force in the load. This is a rubber material, so we need to use large displacement. So go to, make sure you choose the large displacement option here if you do not want to create a param. And then choose my NL out here. Right, so that is set up. Okay. And I'll do another unloading. Okay, so now this is done. If I want to do unloading, let's say I press it. Okay, so these are the force, I think. Okay, so this is the force. This is gonna be, this steel part is gonna push on the rubber. And when this is loading, you push down, and I'll create another step called unloading. Okay, let me do that. I'll duplicate this, and I'll call this unloading. Load. Okay. So unload, instead of having the force here, I'm just going to remove the force. Okay, so there's no force now. It's going to unload, but it will treat this as a separate time step. Has a separate load step until I define this continue nonlinear sub. So there is a continue. Let's see. Yep. So here, this one here, continue nonlinear sub case. So this will actually prompt the second step to continue from the first step. So you need to turn this on. And if it's yes, then this will continue from the previous step, which is the step 1. Otherwise, you'll just treat it as a separate run. That means this is your initial model and then there's no load. Which doesn't make sense, right? So we need to turn this on so that it continues from after we have loaded it and then release it. Okay, so that's what we want to do here. Right, so we need to turn this continue NL sub on for the second step. Okay, first step we don't need because we don't continue from anywhere, right? Then we can put a output request if you want. You can put in your basic displacement, your stress strain, your SPC force if you want to look at reaction forces. Stress here, strain here, you can look at that. Since actually we have contacts here, but it's already defined in the model. There's actually contacts between the two parts here. Even look at the contact force as well. We can also output contact force con F here. Okay. So I guess that's all. Let's look at NL out. NL out is set. We probably want to turn on the non-convergence set to yes as well. So if there's any convergence issue, we will capture that final time step as well. I'm not going to use the load add here for now. So I'm just going to use the exact loading without any scale up. Let's see if this will give us some results. Okay. So let me see if I've missed anything. This is turned on. Okay, so the request ended out for 10 steps here, so it's okay. But the initial time step here is 0.01. So let's see if we can converge at 0.1. Yep, so I guess that's it. So we can run this now. I will export this as a solver deck. No need. Okay. Right, so it's finished. Now let's run this. Okay, hit run. Any questions on the setup? Contacts. Right, there's no curve fitting that's being done here because we directly put in our constants. Okay, so let me show you an example of the out file where we do a curve fitting. You can see the notepad, right? This is a setup where I only have the uniaxial data. Okay, so it's a tension compression data, and this is a stress strain curve. Okay, so we put in this table 1, which is for uniaxial, and refer it in the MATHE. Right, so you can see I'm using Arruda-Boy's model, and this is my Poisson ratio. So you can go for hyperelastics normally 0.495. You can go higher, like what I've done here. It is supposed to give you a better curve fitting if you put higher, but sometimes you'll complain that it's highly unstable. Yeah. So if it's higher than 0.495, you will complain that it's highly unstable. So it depends on whether you can get a good curve fitting. Okay. So I'm using that, and I put in my table 1 here, tab 1. Okay. So I need to have the uniaxial data. So that's the one that is being referred to. And if you remember, Arruda-Boy's is good if you have only uniaxial data. So that's why I'm using Arruda-Boy's here, right? So when it actually map it, this is the stress strain data that I've provided. So this is from the test, okay, this row here. This is from the test, and this is the curve fitting that is done within Optistruct, okay? And based on that, based on the table data that we input, we actually calculate these two constants here that is required for Arruda-Boy's. Okay, so these two constants are required for the Arruda-Boy's. We derive them. So you see the constants are fitted and derived. Okay, and then Optistruct internally will do a test to compare the stress strain that is generated from the derived constants against the testing data. Okay, so you can see how close we are to capture the test data here. Okay. Yep, so this is what I meant. There'll be a warning if you use higher than 0.495. Okay. And what it does is, if you're using curve fitting, you will derive the constants, you will check the stress strain comparing to your input, and you will also check for this material stability here, right? This material stability check, you will check for all the tests whether your material input is stable or not. Okay, so as long as you see this is stable for all directions, then it's safe to use. Okay, if not, then you probably need to switch your material model to something else. Maybe Arruda-Boy's is not good enough. You need to change to other material models. Okay, So this is the material check that we do if you put in your input table from the testing data. Okay. So just want to share this to you. Right. Of course, for our model now, we don't see it because we directly input the constants. So they just use it as it is. Okay. It's slow now. The increment is actually very small. Or maybe because I started with a very large time step. So the initial time step will have effect. Okay, so it will actually determine whether you get a convergence very early on or not. All right. So let's look at we can look at the monitor file. Okay. You can see that the first time step was 0.1 is actually too large. So non-convergence, it cuts back and cut back smaller and cut back smaller. So if you now know that, you will start moving at 0.001. So maybe the next time step that you want to start, if you have tweaked something, you want to rerun again, you probably don't start with 0.1. You start with 0. Like this time step here. Okay. So probably start with 0.001 now. So if the next run, if I want to make sure that the first step is successful, because if a successful first step will help a lot in the convergence. Okay, so you get to converge faster. So probably the next time I run this, I will change this now, the NL pump. Here I probably change it to 0.001. Okay, so this is gonna be this will ensure that the first step will converge, and then you will take it further from there, right? So this is how you can improve the calculation time. Right, so I will just let this run. Probably gonna take a while because the time set's now very small. Okay. In the end, what you get to see is something like this. So slide, you probably see something like this, right? So there'll be no issue here because these are the constants material constants that we have given to them. So you definitely will get converged runs. Okay, so you can try that out. It's better if you have the stress strain data for the 3 tests, which you can input into your model and then test it out and see whether the curve fitting is good to mimic the exact data that you have given to Optistruct. One thing to note is that when you put in your stress strain data, format HE, just going to make HE. It is not exactly stress versus strain. It is stretch ratio versus so it's stress versus stretch ratio. So a stress ratio, it's just, let me show you from here. See if I have it defined here. Yeah, so your stress strain data that you put in is actually it's not exactly stress versus strain, but stress ratio. So your X is stress ratio. So it's engineering stress versus stretch ratio. What is stretch ratio? Is just 1 plus strain. So whatever strain, engineering strain that you have obtained from the test data, you just plus 1. That is your stretch ratio. So you need to convert your data to stretch ratio versus stress versus stretch ratio instead of stress versus strain. So that's the only thing that you need to change from your raw data. Okay. For all the 3 tables here, we will use that stress ratio. Nonlinear geometry. Okay, we have actually touched on this nonlinear geometry. We have actually used it a few times as well. So basically, how do you activate nonlinear geometry? Is basically with this large displacement, right? So you just need to turn on the param either from the param or you set it in the NL pump large displacement, right? Yeah, so large displacement is basically to capture those large deformation, large rotation. If you're doing buckling, definitely to turn on. And also following the follower loads. So we will see this in chapter 4 later on, the next chapter. How do we apply followers? For what are follower loads, and then how do we activate them? Okay. So Geometry nonlinear is basically a change in structural stiffness due to the large deformation that's happening, right? So we need to turn on large displacement here. So this is how you turn it on, either from the param or from the NL pump defined in the subcase, right? Yeah, so it's this example of a large displacement as well. When there's a snap through, right? There's a very huge structural change here because here is probably stiff. Okay, then it's suddenly there's a snap, and then there's suddenly loss of stiffness, and then there is a stiffness in the reverse direction. So, yep. So this is definitely you will require large displacement. If you were to use this just the small displacement formulation, then you probably get a linear curve like this. So it's definitely wrong. Okay. These are the elements that are supporting the large displacement formulation. Okay. Yeah, so your shell solids are all supported. Special elements like bushing, all these are not supported, meaning that you can still run if you turn on large displacement, it will still complete without error, but then it's actually using the small strain formulation to calculate. Okay. But if you have these elements RBE1, which is really seldom used, and ConM, which is also seldom used, then this will not support large displacement. Okay, currently not supported. So don't have to worry about this. Actually, we seldom use this anyway. Okay, we normally, what do we use more? It's what do we use more is this RBE2 here, which is already supported. RBE3 is also supported already. ConM is normally not supported. Seldom. We use ConM2. Okay, so yeah, so these are just mass elements, so you don't really need large displacement for mass elements. Okay, so the mass is considered there, so we don't really need to have any large displacement for the concentrated mass or the lump mass, right? Yeah, membranes are supported. So there are certain shell elements that if you model them as membranes are just skins. You only define in the material in the mat1. Okay, you only define MID1. So if you remember for let me go back to Iberworks. If you define a material for shell elements, okay, or let me rephrase that. If you have a shell element that you want to model, it has just skin, right? Skin means that it just have the stiffness in the bending. You just have bending stiffness, but it doesn't have any stiffness elsewhere. Then you probably need to turn on in the material here. Sorry, not in the material. In the property here, you just need to turn on MID1. Okay, so for MID2 and MID3, you need to check this and then say blank. If you want to model it has skin, okay. If you want to model any shell elements as skin, it cannot have any stiffness in this bending direction, and it cannot have any stiffness in the transverse direction, only in the axial or in plane direction. So MID1 will cover that. That's why you need to put MID2, MID3 to be blank if you were to model a skin, okay. But if not, if it's just a normal thin plate, then you need to turn these two off, okay. So to put it clearer, let me show you in the MID in mat1 here. Okay, so you see here sorry, not mat, P shell. P shell. Shell, right. So if you want to model a shell element has skin, you just need to define MID1, MID2, MID3 will be blank. in normal case, for normal thin plates, MID1 equals to MID2 equals to MID3. Okay, like for example, in the bottom here, you see now here is actually 3 different materials, but in normal case, the thin plates will have all the same material. Okay. Yeah. So even though just model for skin, that's why MID1 needs to be activated. MID2 and MID3 will be blank. All right. So yeah. So let's go back. Membranes are also supported for large displacement. So if you have membranes in your model, then don't worry. It's still supported for large displacement. All right. And this is a P-bush or general spring. We normally don't use this anymore. So we normally have a P-bush. That is the normal P-bush 3D. Okay, so that P-bush you can run without error, but it's not using the large displacement. Okay. So material support, all these materials are supported for large displacement. So don't worry, your Mat HE is supported, Mat S1 is supported. Okay, Mat 1 is supported. Right, and if you use a large displacement as a preload, so remember earlier we talked about preloaded model analysis. So if you want to consider in the first step to have a large displacement, you can do that, and then use that large displacement result as a preloaded result or preloaded model for the model analysis. So you need to define the stat sub preload here to refer to the first step, which is the large displacement. Okay, so meaning to say you can have something like this. Step 1, okay, you run with step 1, you run with large displacement, and it's going to be non-linear. Okay, then second step, you run the model analysis, which will actually use the preloaded results of step 1 here. Okay, so it's going to take this model and run model analysis. Okay, the result of this model run model analysis. But take note that it will only consider the stiffness change. It doesn't really take the end result of this. So meaning that if let's say you have some stresses here, it doesn't really take the stress and then continue to perform a model analysis. You just update the stiffness that's happening to the model and run in the model analysis, right? So it's just a stiffness update rather than the exactly model update. Okay, it's just the stiffness matrix that's going to be updated. Okay. Yep, so you can see something like this. Yeah. So this is the first we run large displacement here. Okay, so there's large displacement in the first step, and refer using this preload here. Okay, so this refers to the first subcase. All right. Same thing here as well. We also have this preload, but this is a model frequency response referring to a NL step. Okay, here is a linear static analysis referred to an NL step, so it's also possible. And here we have a buckling that refers to large displacement also. So buckling, if you remember, we need to refer it to buckling will need to refer to a static subcase, okay, because it's, remember your factor that you calculate, the critical load, okay, is actually the factor, right? Factor times the reference load. Okay, so the reference load comes from the static here. Critical load is what we will calculate here, right? So always need to refer to reference load. This subcase 5 here is the reference load. Okay. But this reference load is also preloaded. So you see this reference load is preloaded. This here is calculated from the first subcase. Okay. So this is how it's connected. All right. Okay. And initial relief is also supported for large displacement. All right. So if you're going to use large displacement with initial relief, we can also do that. All right. Just some notes for you guys. Okay. So now we can try to set up. Actually, we already done large displacement already. Basically, it's very easy to turn on. Just either turn on from the param or you turn on from the NL pump. Okay, so there's nothing much to it, but you see difference whether you turn it on and off, turn it on or off. So if you perform this exercise 3A, you can actually check the results. There's another exercise here. You can also try this. Basically, the model is already set up, context all set up because we haven't touched on contact yet. But here the models all set up. All you need to do to set between the two models here. One you run with small displacement, the other one you turn on large displacement. So you get to see results like this. Small displacement is going to be pretty weird, right? Deformation is large and so on. But if you turn on large displacement, we actually get better capture of the behavior, right? Of the local strain especially. Right? So you can try this. Try to set this up as well. Right. So I won't go too detailed because basically it's pretty easy setup for large displacement. Nothing much there. Right. So let's go on the Q&A. Which statements are true again? So let's go one by one. Param large displacement activates large displacement for all subcases. Okay, so here it's talking about if let's say you have 3 subcases, right? Subcase 1, subcase 2, subcase 3. All of them are, imagine all of them are non-linear static runs, NL stat runs, okay? Of course, you know under NL stat, in the subcase, you need to define the NL pump, right? So there are 2 ways to activate large displacement, either through NL pump, where you turn on large displacement here, okay? Or you use a param card to define the large displacement, right? So you can use either one to turn on large displacement. The difference is if you turn on through the subcase, so this will actually just turn on the large displacement for subcase 1. For subcase 2, you need to turn on again the NL pump there if you want to use large displacement for subcase 2, okay, and so on for subcase 3. But if you define it using the NL, and if you define it using the param card here, param large displacement 1, this is going to turn on for all of them, okay? So yes, it will turn on large displacement for all subcases, only if they are, caveat here, only if they are NL stat subcases, okay? Of course, if they're not NL stat, then nothing is going to be done, okay? If it's just a linear static, then probably, and param here won't do anything, okay? Number 2, initial relief is useful if unbalanced force exists. So this is a recap of what we have learned in the last training. What's initial relief for? Initial relief is applied where we apply a imaginary force to balance out the force that's being applied to the model, especially when the model doesn't have any constraint to it. Okay, so yes, this is true. Okay. Statement 3, a change in structural stiffness is geometric nonlinear. Okay, so yeah, we learned this in the beginning. Nonlinear geometry is actually change in structural stiffness, right? So remember what we have with what we had earlier with this one, the snap through here. Okay, so here is actually a change in stiffness. So nonlinear geometric is actually just change in the stiffness here. First probably stiff, then when it experiences that snap through, then suddenly there's a drop in stiffness, right? There's a drop in stiffness here. So no force is required. So there's a drop in stiffness, and then there's a stiffness change where there's stiffness in the opposite direction. Okay. So this is yep. So geometric nonlinear deals with stiffness change. Okay. So the statement just now was true as well. So all the statements are true for the question this question here. Okay, so all the statements here are true. All right. Next chapter is nonlinear loads. Okay, and basically we're going to talk how do we use this follower load. So I've mentioned this earlier in the previous chapter of nonlinear geometry. Nonlinear geometry is actually used to define follower loads. So we'll see what's follower load, right? So follower load is a loading that would change. Sorry, let me just double check the recording first. Okay. So follower is a load that would change with respect to the change in geometry. Okay. So if you define your load at the beginning, that is in this Z direction, and if there's no follower load present, even though now the beam has already bent by a lot, there's a very large displacement already, and it's actually caused a change in the original geometry, right? If your load doesn't follow the change of the geometry, that's why it's without follower, it doesn't follow the change, then your force will always be just in the Z direction, which is downwards, right? But if your force has follower load enabled, as the geometry is bending, you would see that your force will then follow that geometry change. Okay, so that's the purpose of turning on that follower load. Okay. So you have to turn that on, you can just use the param there. And then this will enable that follower load. Okay. And of course, this has to be used together with large displacement. So having this turned on, but you don't have large displacement doesn't make sense. So you need to turn on the param large displacement also. Right. Right. So it's an example where this is my loading. Okay. So if I don't turn on the follower load, it's just going to just drag this beam all the way following this direction here. Okay. But if I have the follower load on, because has these changes, as I define my force to be always normal to this initial phase, has now the phase has now this beam has been bent. My force will still keep to be normal to this phase here, right? So that's where follower load will have effect. Okay, imagine this is another example. Imagine if let's say pressure can also be follower on or off, right? As you know, pressure, let's say if this is a rubber, right, and pressure is always directed normal to the face. If the follower load is not turned on, your direction cannot change, right? So it's always normal to the initial phase. Initial phase is flat, so it's always normal. That's why it pushes this up, the pressure. But if this is a rubber, of course, when it expands, you become a balloon, for example, you will see that the direction of the pressure is always normal to the element. So if the element is suddenly now changes direction, is no longer flat, then the pressure will also follow that. Okay, so that's an example of follower pressure. Okay. Something to note, only those elements supported for large displacements are supported for follower load. Of course, we need large displacement, right? So if large displacement doesn't happen, then follower load won't happen. Okay. Limitation here, we have all these forces here can be used for follower load. So we need to define all this. We actually will, in our exercise later, we actually use force 1. And we have the follower load in force 1 here. Okay. If you're using continue nonlinear sub, right? Continue nonlinear sub, then the follower load option must be the same. Means if you turn on in the first subcase, there is a follower load. Second subcase, you need to turn on as well. Okay. All right. Hope you guys can still hear me. It's raining pretty heavily here. Right. So this is if you're defining follower load with force, then you need to turn on this follower load here. Okay, so there's one follower option that can be turned on when you're using the force card, and also moment card as well. There'll be a follower here, so you need to turn that on also. Okay, basically just turn it on or off. It's as simple as that. All right. Preload 2. If you're using preload 2, then you need to turn on from the param. So remember there are two ways to turn on. One is from the param. So if you're using preload, the way to turn it on is by using this param card here. Okay, so this will activate the pressure, and the pressure change will change according to the surface. Okay, so normally we use follower pressure here 1, so this will actually update. All right. So if you're using preload, doesn't matter preload 2 or preload 4, you need to turn on the param follower if you don't use the follower load for pressure. Okay. All right. So I will demonstrate this exercise now on how to set up. Here we're going to use force 1. So there'll be two models here. There'll be two models. One is first we run without follower load, and the other one with follower load. Okay. Yep. So let's do that. If you let's just look at the exercise first. If you look at the manual, okay, so we are going to use this as the standard. Then we will define with force 1 here. Okay, so when you define force 1, and then we also set the param in the follower load to 1 as well to turn that on. So we need to set both of them on. Okay, so that's just a reminder. Let me go straight to the model. Let me just check if it's okay, FEM. So I'll import the FEM file. Okay. Right. So it's just a curved beam. There's a RBA at both ends. One will be the support, the other one will be a where we apply the loads. Okay. So let me just check on the ID first. This is 85, 86. Okay. So I'll just follow the convention here. Oh, the numbering is different already. Anyway, I'll define 85 at the bottom to be the SPC, right? 85 at the bottom to be SPC, and then the other side 86 to be the load application. Okay, so the model doesn't have anything, doesn't even have property and material yet, right? So first step, let's define the material first. I'm just going to use steel, right? So I'm going to create material first. Use a steel material, just put in the standard. For this one, I'm just going to use the linear material. And then I'll create another property for that beam here. Okay, so it's going to be a P solid. And I'll put in my material here. Okay, so property, and then define it to the component. Beam property, yep. And I need the load collector for the SPC. Since no load collector is created yet, I can just straight away come to here. It will auto create itself. So create a constraint for this point here. Oops. No, it's Right, so I'm going to create a constraint for this point to log all 6 SPC created at here for all 6 degrees of freedom. Create, right, 1 to 6, and double check on that. Here, load collector, we have this, just rename this to SPC, right? And then I have the other side, the force. There's something special about the force here. Let me just, it's gonna be magnitude of 100 in this direction. Okay, so I do not want the force to be grouped together with this SPC here, so I will need to create another one. I can just duplicate this. Okay, then I call this force. Okay, but cut image for force SPC is always none. Okay, there's no cut image for that, so it's okay. And now I will create that force under here. Click on this icon. All right, and here I'm going to use force 1 because force 1 allows me to define the direction. Okay, so force 1, the direction of the force 1 will always change because we need to define the direction. Okay, so here it's going to be applied on this node. Magnitude is 100. Okay, the direction is following this one here. So I'm just going to take this one and this one. Okay, so, oops, sorry. This is the force, this is the direction. Okay. Right, and create. Right, so this force here is always going to be based on the coordinates of these two. So as these two experience large displacement, the force is going to follow the coordinates here. Okay, so that's force defined, force 1. Of course, you need to turn on the 2 params, right? One is the large displacement. Let's turn that on first. Large displacement on, and follower load on. Okay, so that's all you need to do to have follower load on. All right. Let's just change the color so that we can differentiate. And then, of course, you need your cards for the NL pump. So all your nonlinear cards need to be created as well. NL pump, let's just do 0.1. Then we do a NL out as well. Oops. NL out. Rename this to NL pump. So NL out, I'll just simply do a 10 step here. Okay. All right, so let's create the load step now. Just call this loading step. It will be NL stat. SPC is my SPC there. Loading will be my force 1, which is here. NL pump, I don't need to use the large displacement, right? Because I already turned on the param, so I can just use it here. And then the NL out. Okay, so you can try this one. Okay, that's good enough. We can run this. I'll save as, this is with large displacement. Or let me just put follower. Okay, this is with follower load. Right, so run this. Okay, so for comparison, I will run another one. Another one without follower load. Okay, I'll just copy and paste. Let me just turn this off. Let's see if this will happen. Okay, so I just turn off the follower load parameter. And we'll run that. So this is no follower. Right, so I'll open compute console again to run that file. No follower. Okay, so let's open the file first with the follower load. Okay, so you see this is the result. Okay, displacement. And let's open another window where we run. Should be done by now. Okay. Oops. Let's open no follower. Okay, so with and without follower load. See, this is the final result. You already see it already. So let me turn on displacement and synchronize them. Okay. So you can see the difference between with and without follower load, right? So one is always gonna be normal or perpendicular to the surface there. The other one, the direction is always fixed, so you tend to pull it after it has surpassed a certain displacement. You will actually drag the entire or pull the entire beam in that direction. Okay. Okay, so you can see the difference there. Okay, so with and without follower load. So remember to turn that on if you really need it, especially if you are dealing with large displacement. Okay, any questions? Really easy to set up. Yeah. All right, so next topic is multi-loads, where you have a so far we have done, we only deal with a single step load, but if you have double step, like what we did earlier with the rubber, where there are two steps, right? One is loading, the other unloading. So if you want to do a continuation, you need to turn on this continue nonlinear sub here. Okay. But there are other ways. You can use pretensioning, preloading, as well time dependent loading. So there are a few ways to create multi-step. Here is a summary of what's going to happen if you use different steps or different methods to simulate your multi-step, right? If you use a continuous nonlinear sub, that's why I like this the most. You will actually carry over all the stress, strain, and displacement. So step one, the end result of step one is going to be carried over to the initial step or step two. Okay, so this is good, right? If you do a time dependent loading, it's also going to carry over. Okay, so time dependent loading is like in one step you define from time 0 to 0.5, you have a loading, 0.5 to 1, you have unloading. Okay, so of course that will carry over those stress, strain, and displacement as well. Okay, if you're doing pretension, it will carry over as well. But if you're doing preload, so the stats up preload that I mentioned earlier, the preloaded model analysis, for example, it doesn't carry over the stress, strain, and displacement. It just carry over the stiffness. Okay, so stiffness matrix is going to be updated if you're using a preload. But if you're doing pretension, then yes, the stress strain also will be carried over. Okay. Yep. So if this also depends, you can use continue nonlinear sub if both your sub cases are nonlinear. So step 1 is nonlinear, step 2 has to be nonlinear also. Okay. Yep. If you're doing time dependent loading, you can do all in just a single step. You don't need a second step. So that's the difference here, right? It can be linear here, it can be non-linear here as well. Pretension as well, it can be linear, can be non-linear, preloading as well. Okay. So you can see different use cases where you want to use it, right? Right, here's just an example. First step, we have the force pushing down, and then the second step, we have a force that is in the lateral direction. Okay, so if you want to do this, you need to use, if they are non-linear, you can use continue non-linear sub. Okay, so you can use continue non-linear sub, and when you define that, you can define it a few ways, especially if you are editing the text file or editing the input deck, right? But if not, then you just set it up in HyperWorks here. All you need to do to, oops, let me see where's my HyperWorks. Okay, to set up in HyperWorks, all you need to do is define it here. Continue non-linear sub. Yeah. To activate that, just continue non-linear sub, and then choose. You can choose yes. Yes means that you will continue from the previous step, or you can also refer it to a particular step. So let's say step 3 will refer to step 1. You can set here subcase ID to be the particular step. Okay, so you can do that also. Either you use yes or point it directly to a subcase ID. Right. So yeah, so here's an example where it refer directly to a subcase ID. Here you just have the yes that is going to actually refer back to the preceding or the previous subcase. Right. If you do not use continue non-linear sub, SPC has the option to have this fixed as well. So in a way, if you're using continue non-linear sub, then you don't need to use F already, right? So F is gonna fixed option is similar to saying maintaining the condition after you have compress it and then use it for the second step. Okay, but now because we have continued non-linear sub, so you don't really need to define the fixed flag here in this SPC card. Previously, we need to define that. Okay. So now you don't actually need to do this. If you're using multiple step defined in a loading history, in a curve here, you can define it this way. So this loading and then there's unloading. Okay, so define all the steps inside inside a curve. Okay, so remember the automatic time increment. So we always run each step is going to be from 0 to 1. Okay, so you need to readjust your or scale up your time here so that your load will be at 0.5 is 50% loading, and then 0.5 after that is the second 50%. Okay, so you need to consider this. Okay. Okay, so basically very easy, just use this tload 1 to define it, right? Basically just define your you need to define your time here or load increment. For example, here 0, where is the loading, 0.5, where is the percentage of load, and then 1 is where is the loading. So define it and then put it under here. Okay, TID here. Yep. So for tload 1, we will learn this. We will use this a lot in our linear dynamics topic later on, tload 1. So you can see here we actually need to define the type of the type of loading. So whether you're loading a load or you're loading displacement, you need to define it here. What's the type? Okay. Yeah, basically this is important, right? And then the another adapt card, we have touched this earlier, where we actually introduced the stabilize. So there are some other things that you can also implement to control your run. For example, we touched a bit the number of cutbacks, the maximum time increment allowed, or minimum time increment allowed. Okay, so if you set a minimum time increment allowed, means that you cannot go lower than that. So let me show you from one of the runs here. So you can see this is the current time increment. It's really pretty easy lah. So it's only all fixed already 0.1. But if it has some issues with convergence, which I can show you from one of the examples that we ran earlier, especially this one where we have convergence issue. Or let's just open the monitor file. Okay, so you can see this is the current time step increment. You can see it's pretty small, all the way down to 1e minus 7, all the way down to e minus 7, right? So it's a very small time step. If let's say if you did set your DT min here, let's say to be 1e minus 4, then it won't go down to that stage. Once you have reached that 1e minus 4, if it cannot converge, remember, if we cannot converge, we need to reduce it 25% of the current loading. So if you cannot converge at 1e minus 4, it actually needs to go down to quarter of that. Okay, so it's going to go to 0.25 e minus 4 or 2.5 e minus 5. Okay, so you need to go down lower. But because of the minimum time increment that we have set, it doesn't allow that. So it will actually fail. And it will complain that minimum time increment has been reached. Okay, so this is useful to set so that you don't have to wait until the run to be very small and actually it won't converge. Maybe it continues to run at the pace of e minus 7, e minus 8, and takes forever to complete, right? So you might not want to wait until so long to find out that okay, there's actually some modeling mistake. There might be some contact error in my model before you go and fix it and then run again. Okay, so you probably want to set it, let's say 1e minus 4. Once you reach to that, if still cannot converge, then it says I know there's something wrong in my model already. Okay, so for example, in this case here, which I ran earlier, it went down all the way to 1e minus 7, and it stays that way for 1e minus 6, e minus 6, e minus 6, e minus 7, right? So instead of waiting here, I can say this is already 1e minus 4, right? If I put in my DT min to be 1e minus 4, once it has reached this, it still cannot converge, it try to go down lower, then it will tell me you fail already. So I know there's something wrong in my model at very early stage. I don't need to wait until so long or need to know that at the 43rd increment, then you know there's something wrong with my model. Okay, so this will be good for you to help you to save some time instead of waiting for so long, and then in the end find out your model cannot converge, something wrong with the model. You can take the countermeasure steps early on, okay, to fix the model. Right. So that's the purpose of DT min. DT max is also the same, but it's mainly to control the maximum time increment, right? So you don't have too large, because that will also affect the convergence, right? Right, so the direct option here, you can see here's on direct. By default, we turn on the adaptive time increment scheme. So that's why you see that we have the cutbacks, and then you reduce the time step and then try to converge, right? So by default, this is turned on. But if you do not want that, you can set to direct, means that it will just run. If it encounters some error, it won't cut back, and then you will just say you fail, right? So with direct, it will just directly stop and saying that it will fail. So Yeah, for example here, 0.1 increment it can complete, 0.2 try to run, then it encountered some error. It won't go to some cutbacks already. It definitely immediately tell you that it has failed. Okay, so there's pros and cons. Pro is that you get to find out earlier on if your model is failing. But then sometimes allowing cutbacks can allow your model to converge also. So this is good. You can go and fix your model. But sometimes if your model is highly unstable, you need to allow that initial cutback and then also try to introduce some energy to it. Okay. So this one, yeah, I seldom use it because I will prefer to try to complete itself using the using that time increment adaptive time increment scheme rather than using a fixed scheme. Okay. Yeah. So it was done when you're using a non-converge. You actually run with a smaller time step and try to converge, right? Okay. The set. Then NL out controls the output of your results, right? So whether you want to output at a specific time increment, or you can choose now we have the time and frequency here as well, right? Frequency and time here as well. So we can also turn on this one, save non-convergence, so that we get the final step. If there's a non-convergence and the run failed due to that, we get the final step being output as well. So normally it's best to set this as a save non-convergence. By default, if you turn on NL out, it's going to set it to yes anyway. This is a new practice. Previously it's not. Okay. So yeah. One thing to note, the NL out is when we will specify NL out. Let me go to Hyperbox here. If you turn on NL out, right? Right. If you turn on NL out and let's say you turn on NL out, you don't specify this on. Save non-convergence is going to be yes by default. Okay. But if you check this here, by default here is going to be no lah. So this is default in Hypermesh itself or Hyperbox itself. If you turn this to be no, if you just turn this on, it's going to be shown no here. So you need to be careful. You need to turn this back on to yes. Okay, so that this no here is actually the default in Hyperbox or Hypermesh. So you need to double check that. But if you just leave it here to be blank, by default it's going to be turned on when you have the NL cut, NL out cut. Okay, so either you do this, or if you want to really check this, make sure you turn this to yes. Right, that's the only thing that you need to be aware of. Okay. Yep. So that is all for this short topic here on follower load and also the non-linear loadings. Okay. So this is an example where we have the direct there, whether it's auto or fixed, right? So if it's if you set it to fixed, when it encounters some convergence issue, it will just die off there. Okay. You just end the simulation, cannot converge because you don't allow it to even cut back. So if you allow it to cut back, by default, we allow that, which is using the auto. So it will cut back and try to achieve convergence. Okay, so that's so that's why I prefer to leave it like that instead of you choosing direct. Okay. Why people choose direct? Previously, for NL out, okay, previously NL out, we cannot output according to time. So you cannot define it to output at time equals to 0.1, time equals to 0.2. So if they want our solution to output at that specific time, they'll choose direct to be on. So when direct is on, you don't allow it to cut back. So you will need to complete at 0.1, 0.2, and then output the results. Okay, if the run cannot output that, then you'll fail. But now with the new NL out, you can couple it together with this one here, so you can have the adaptive time step increment, and then you can also output at a specific time that you want. All right, so it's more flexible now comparing to last time where we just where we don't have the option in NL out. Right, so now we have that. So I would just advise you to leave the NL adapt here to be auto, the direct here to be auto. Okay, and then you request the output that you want in NL out, right? Welcome back to day 2. Yesterday we have talked about nonlinear in terms of nonlinear geometry and nonlinear material. So today we are gonna focus more on context, right? And most of the time when there is a non-convergence issue or there's some difficulty in convergence, is mainly due to context, especially if you have a lot of context in your model and if it involves large displacement. So yeah, normally those are the things that will cause you some debugging time, right? So why do we need context? Of course, if you don't define context, then parts can actually penetrate each other. So we need context to make sure that they don't penetrate, right? And of course, with contact, you can also have sliding, frictional sliding, and so on, right? Yeah, several difficulties as mentioned. If there's large changes, means if there's a really large displacement that cause some areas to have contact in the beginning, and then suddenly there isn't any contact. So those type of simulation might cause some difficulties in convergence. Okay, if there's a change in stiffness, suddenly there's a rubber, and then it goes into something like a steel material. So those will cause some difficulty in convergence as well. If it's highly non-linear, right? If your material is very soft, like for example rubber, those will have some difficulties in convergence. And also if you have thermal conductance. Okay. So basically the contact is defined with this contact card here. Okay, this is what you will see if you open the input deck. Of course, if you open it from the GUI, from HyperWorks itself, it's going to be different. There are a lot, as you see here, there are a lot of items that we can actually define for contact, and we will need to go through all of them, because all of them will actually give you different settings to the contact, and some will actually help in the convergence of your nonlinear analysis. Okay, so the basic ones are just your we'll see later that contact can actually be defined 3 ways. You either define it directly by putting in your static friction coefficient, or you can also define it using type. So we'll learn what are the types of contacts, and the other way is to use a property for contact. We call it pcon. Okay, so there are 3 ways to actually define contacts, or defining the settings for the contacts. Okay, then we will need to put in our slave and also our master, right? So what's our slave? This is slave surface ID, and then the master surface ID, right? And also, of course, the orientation of your master, because if you're talking about a shell elements can have both sides, right? So you need to define whether which side is actually pointing towards the contacting surface. Then there are some other options available. Search distance. This is gonna generate that contact. You will search based on whatever distance that you've put there. Okay, and then establish that contact at the beginning. So search distance is important. If let's say if your gap is too big and the search distance that you put here is too small, even though you have created the surface saying this is surface 1 will be in contact with surface 2, but if the search distance is too small, then it will not establish that contact as well. Okay. Then we have smooth. Smooth is more for to make your contact contour look better in during your post processing. So some areas, especially if you're using the node to surface contact, then the contact contour might be a bit jagged. So if you use smooth here, then it's going to smoothen out. Okay. Of course, then these are the settings for the smoothing. Right. So this is the search distance. Search distance, the way to define, if you don't define search distance, we're going to use automatically. Usually is based on the mesh size of the master surface. So if let's say a master surface is meshed with 5 mm, then the search distance is going to be 5 mm. Okay. But if you want to specifically define that search distance, you need to consider the gap here. Okay. Consider, you don't have to put in the exact gap here. So for example, now this, I have two sheets here, or two shell surface. One is the shell mid plane here, the other is the shell mid plane at the bottom here. Okay, so they are shell elements, but both of them have a thickness of 2 mm. Okay, so when it's projected up and down, you get actually 1 mm here, 1 mm here. So the actual gap between them is actually 3 mm. So as long as you put your search distance to be larger than the actual gap, this is the geometrical gap, which is what you will see in the HyperWorks, right? You see just from the shell elements to the next shell elements is 5 mm. But the actual gap, because we have to consider the thickness as well, the actual gap is actually just 3 mm, right? So if you put your search distance to be 3 mm, then we will establish that contact. Okay. If you, of course, even if you put 5, you can still establish that. It's no problem. But you just have to be careful, because if let's say this is the actual part here, but let's say if it's assigned, if in the other region is extended like this, okay, where now the actual gap between them is 5 mm, then it will establish contact for this area here as well. So you have to be careful, especially if your part has varying thickness or a non-uniform feature. Okay, that means it is something like this, where there is actually a step. In this case, you also establish, if this is 5 mm, the actual gap is 5 mm, you establish that contact as well. But in fact, what all you want to do is actually establish contact in this region only, right? So you have to be careful with search distance. You can put more, but that is only if you are sure that your the thickness is constant, and then all the areas are also in uniform plane, right? Okay, so yeah, so here is just an explanation of how we actually generate the contact, right? For contacts in Optistruct, we actually follow this penalty formulation. Okay, so has the distance between the two slave and master surface becomes smaller, and when it touches, we actually establish that we actually give in a factor here to simulate that contact. Okay, so that's the penalty that we actually put in to simulate that contact. So the more that it penetrates, right? First, the more that it penetrates here, you see, the higher the force is going to be, the contact force. Okay. So the higher the penetration, the higher the contact force is going to be. Right. We are using, by default, we're using hard contact here. Okay. Of course, we can actually scale this penalty stiffness. Right? By default, it's going to be hard contact. Means if there's a contact, that means there is going to be contact force that is going to be exerted on both the contacting surfaces, right? But if you are, some of the times you might find that hard contact will actually cause difficulty in convergence, right? It might be difficult to converge with hard contact. You can actually change the stiffness of that penalty here. Okay, so you can actually put it lower. then with that you can actually your slope won't be so steep like this lah, right? So there will be a slope to it, and you can also adjust the penalty stiffness here. So there are a few ways. One, you can leave it at default, okay, or you can also put it penalty stiffness equals to high or penalty stiffness to low. Okay, so those options are available, or you can also directly put in the value that you want. Okay, so we'll talk about this stiffness later, right? Yeah, so this is the stiffness here is defined under the property for context, pcont, and it's defined under the stiffness here. So you can either put in soft, you can put in hard. Soft means that soft means that it will allow some penetration, some degree of penetration. Okay, hard contact means it will definitely will not penetrate, but then sometimes it might cause some error, some difficulty in convergence. Okay, of course, if you find that both your master and slave surface are having too many or too much penetration, then you can use the hard here. But if you're facing convergence issue, then we recommend to use the soft. Okay, otherwise just use the auto here. Okay, by default we just leave it as auto. Of course, you can also put in your values here. So what are the what scale factor that you want to put in? You can put in. You can manipulate yourself as well, right? Okay. So yeah. So these are the topics that we're going to cover in context. We first learn about type of context, the orientation, the discretization, whether it's node to surface, surface to surface, or node to node. Then we have some advanced features like clearance, smooth, adjust, and also the track, which is important to determine if, especially if you are using a very large displacement simulation, right? So we go to them one by one. First, we learn about the contact type first. Contact type, as I mentioned earlier, we can define it using three ways, either using type, by putting in the actual static friction coefficient, or by assigning to a pcon. Okay, so we assign the PID 7 here, property ID 7, which actually refers to a pcon cut, right? So there are three ways to define your contact, right? And specifically now we are going to look at this type here, right? So for type, you will see that we can actually have three options here. One is sliding, slide contact, sticking contact, and then the other is freeze contact, right? So when you are assigning your contacts to be sliding, it will allow a sliding on the surface, means it's going to be the two parts here are just going to slide, right, along the surface here, but it cannot penetrate, it cannot separate, right? So if you need it separate, you need to define it using the pcon. Okay, so sliding here is going to just allow this one. So this here is not allowed. Okay, of course, with sliding, you can either define it with frictional sliding or non-friction. So you can define your friction there. Sorry, for sliding here, it will be frictionless unless you use this one here. Okay, if you use this and define it, the friction here, then it's going to be friction. Otherwise, here it's going to be frictionless sliding. Okay. Then we have sticking. Sticking means that your part may be separated at first, right? Your part may be separated at first, but during the simulation, there is a force that pushes this block A down onto the surface, and as it touches, then if your contact is sticking, that means it will not have, it will build after contact is established between them. After there is contact established between them, this part can no longer separate. Okay, this part can no longer separate. So yeah, imagine you can imagine this like there's a glue here that sticks the two parts together. After that, after you have pasted them together, you cannot separate the parts out. Okay, so that's sticking here, right? Then there is a freeze as well. So freeze is you just establish contact at the very beginning, and then it will be bonded throughout the entire simulation. So there's the freeze contact, right? So it'll be contacts will be closed at all times, no matter what's the distance. Here we say no matter what's the distance because even if you have, let's say if your part has a very large gap like this, okay, let's say the gap here is 5 mm, right? 5 mm gap. If you put your search distance here to be 5 mm, we will establish that contact even though you see there's actual gap here. So if your contact is freeze, right? But because your search distance is 5 mm, it will search between the slave and master surface and you see that okay, this gap is 5 mm, I can establish contact. So it will establish contact even though there's actual gap. So it will be closed at all times and no matter what's the distance between them. Okay, because it's governed by this search distance here. Somebody's coming in. Okay. All right. So yeah, be careful with freeze, especially if your parts are having gap at the beginning. You have to be careful because it will actually establish that contact already. Okay, so just take note of this this freeze together with this search distance here. Right. Similar to freeze, we actually have another contact type which is called tie, or in other words, tie contact. So tie here is similar to freeze. The function or the method or when to use it is the same. When you want to establish a bonded contact from the very beginning throughout the simulation, it cannot separate. Then tie and freeze functions the same. Okay. The only difference is tie will actually tie. If you define it tie, we will actually convert it internally to a contact that is similar to freeze contact. Okay, so tie is actually from another solver, is from Abacus. But if you define tie here as well, we actually convert it internally to freeze contact. Right, so it's basically the same thing. But for tie, there's another option to use another type of formulation that is using the MPC constraint. Okay, so that you can define it separately. But functionality wise, it's the same between tie and freeze contact. You're just going to establish a bonded contact between them. Okay. So this load case will help you understand more on the difference between stick, freeze, and slide. Right. So imagine subcase one. Okay, these two beams here, the orange and the purple beam, they are just touching each other. They are not the contact interface between them. We define it using either stick, freeze, or slide. Okay, and then in the subcase one, in the first subcase, we put a force that is pushing it down. Okay, pushing the orange beam down. Subcase two will then introduce a second force in the y direction. Okay, and then the third subcase will be a force. We remove both of these two forces and then introduce a z force that pulls the orange beam up. Okay, so these are the three subcases. They're continuous, right? Subcase one, subcase two, and subcase three. Yep. Anything? Right. So if we are using slide, you see, right? Slide when I. Yep. Anything? So for subcase, subcase 1, when you push it down, you see when you push it down, it slides, right? There's a sliding between them, and then subcase 2, you see that you actually push it aside, right? And then subcase 3, when we pull it up, you will actually separate. Okay, so that's a slide. And if you use a stick contact, you'll see that after it has touch, okay, you'll be sticking, and then it will not separate even if it is pushed to the side. But if your separation is on and we pull it up, then it will actually separate. So there's a setting for separation as well. If your separation flag is turned on, you can separate. Okay, but for freeze is a different thing. So it's going to be contacting no matter what the force is. Okay, so there's a difference between slide, stick, and then freeze. Okay, so depending on your use case, you might need to use a different type of contacts for different areas. Okay, so we can define frictional, the frictional contact for sliding is defined like this. Okay, as soon as the force exceeds that critical frictional force, then we will actually slide it. Right. Yep. So this is mainly used in the sliding. When do we actually start? When does the part actually start to move? Is all depending on the frictional contact that you define, of course. Nothing much to this. We can just this is just theoretical to help you understand the penalty that we actually introduce to sliding. Okay, so it's defined using these two here, right? Where's your static friction and then where is your kinetic, and it's all defined under the P-con cut here, right? So P-con cut, you see under P-con cut there's a separation here as well. Okay, so here this is just a flag whether separation is allowed or not. Okay. This is just for your information. When we are actually solving any non-linear, we actually use the unsymmetric solver, the MUM solver, we call it, right? So you don't have to do anything to this. We actually turn this on automatically. Once we detect that it's a non-linear static, we will actually turn this on. But you have the option to turn this off. You can use this param here to turn it off if you do not want to use the MUM solver, but it's on by default, so we just suggest you to just stick to the default. Okay. Right. So of course there will be difference if there's a frictional contact with and without friction. So this is just to demonstrate the difference, okay. So depending on whether you need friction or not, of course, in most cases you definitely need some friction. And in fact, if you introduce a little bit of friction, let's say if even your part, if your part you want to simulate it has a non-friction, but sometimes it might be harder to converge. Okay, so as soon as you introduce a bit of frictional, you introduce a small value of friction coefficient, then it will be easier to converge. Okay, so you can also try that if, let's say, you're using sliding contact with no friction and you're finding it hard to converge, you might want to just change it to the friction coefficient, and then just assign a small value of friction there. Okay. So that's the type of contact. Next, we move on to the orientation, right? So orientation is defined here in this card. in the contact card with this M orient, it defines the actually the which face of the master surface is actually facing that contacting object. Okay, so normally we follow the normal of the elements. We follow the normal of elements. That's why it's normally normal here, but we have the option to do a reverse normal as well. So you can either reverse the orientation of your elements, or you can also reverse this orientation of this M orient here. So you have two options. Either you reverse the element normals or reverse this one. So if you remember, if you let me try to read something in. Let me see if we have some shell elements. Yesterday, I think this one is shell. Okay. Right. So remember your normals. When you check for normals, you can see that. Let me use vector display. Okay. So you remember your normals. Now the element normals are actually pointing downwards. So if I generate the contact later on, it's going to follow the direction of this arrow here. Okay. But if you use, of course, that is if your M orient is norm. But if it's reverse norm, then it's going to be the reverse of the arrow here. Okay, so you need to check your element normals first before you start creating the contact. Okay, of course, after that, if you see that the contact generated is not in the direction that you want, you can just go to M orient here to either to change it to reverse norm, or you can also do a reverse here. Okay, so either you change the element orientation or you change the contact orientation. Right. Okay. But do take note that for solid elements, the M orient is ignored because we always push out. Okay, so you will if let's say for example a ball, the orientation of the contact is going to be outwards, right? It cannot be inwards. So don't have to worry about if you are using solid elements. Okay, but for shell, yes, you need to take note of this. Okay. Then there are some other special cases where you have an open gap, right? That means there's a gap at the beginning, right? It's initially open, and then there might be overlap as well. So if let's say you want to, your surfaces, you didn't solve the penetration, you didn't move the you didn't move the slave surface up, then you probably need to define overlap there to tell that it's actually overlapping, right? So these two are seldom used. Open gap is common, but then normally we also use a normal most of the time, and reverse normal in case your contact or your element orientation is in the reverse. Okay, so just need to define this. By default, it's going to be open gap because we always assume that it's going to be initially open. That's why the search distance is there to help to establish a contact, and the direction will always be pushing towards outwards. Means that the master and the slave will always be like against each other, right? So yeah, you can stick to the default. Of course, if you're using solid elements, then you don't have to be worry about this because solid elements will always be pushing outwards. Okay, so that is the safest. Okay, then we have next we go into discretization. All right, what type of surface, what type of contact is defined for your slave and master? Okay, so the first one defines the first letter here is for the slave side. The second letter here is for, after the 2 is for the master side. Okay, so how do you define your slave and master? All right, so yeah, we just have node to surface, surface to surface, node to node, right? If your yeah, there are some defaults here. If you're using freeze contact, there's going to be surface to surface. Okay, if your slave surface is defined with surface, so we will learn later on. There are two ways to represent any slave surface, either with by selecting the elements to be inside that surface set, or to place all the nodes inside the surface set. So if you place the nodes inside the surface set, then the freeze contact generated will be node to surface. But if you use a set that defines the elements, then it's going to become surface to surface, right? So yeah, basically this is the general rule that we use also lah. If you want node to surface, then of course it's easier to choose all the nodes in the set. If you want surface to surface, that's easier to choose all the elements in the set. Okay. Yep, nothing much here. Yep, there is a difference when you choose surface to surface and node to surface. Sometimes surface to surface is the best because it will give you a smoother contour, right? But node to surface sometimes it's easier to converge, right? So sometimes if you're having difficulty to solve surface to surface contacts, then you might want to switch to node to surface. Okay, you can try this trick here. Right. So this is how we establish that contact. If you use node to surface, each of the node will project downwards to find the master surface. Okay, so that's why it's called node to surface, right? And once it projects down, the projection length and everything is also due to the search distance. As long as the search distance is enough, it can project down and manage to find a master surface. It will establish that contact. We call it that contact element. Okay, we call it element. We call it contact element, but we don't really see it. Okay, we cannot really see it. It's just a formulation that defines the contact between the node and the master surface. All right. Yeah, so it's based on the search distance, so it's important to set your search distance right. If normal projection is not found, then we will also try to find within 30 degrees, right? So sometimes your part might not be parallel. The master surface and the master and slave surface might not be parallel. So we actually can go up to 30 degrees, right? Okay, once the master is found, then we will establish that contact element. All right. Okay, so this is just some notes that is internally, right? So if this is just for your knowledge, you don't really have to pay too much attention to it. But for small displacement, we actually convert the contact with a C gap. Then large displacement, we use a different type of element that is different from C gap. So it's just internally what's happening in the background. You don't really need to care about this. Okay. Just know that contacts will work for both small displacement and large displacement as well. Okay. Yeah, nothing much here. Then this is for surface to surface. So surface to surface is the entire surface of the slave is going to be projected downwards and find a master, right? So still it's going to generate 4 because it's still based on the node. Imagine that we still use the node to find the master surface, and then but for one, because this is surface to surface, so we consider all 4 elements, all 4 nodes. That's why there are 4 contact elements here. Okay, so it's like more projection downwards to find, to search for that master surface, right? Yeah, and means that here, as long as, let's say, if we base on the nodes to project downwards, but as long as one of the nodes project downwards can find it, then we assume that the contact established. Okay, so even like, let me draw something like this. Let's say if this is the master surface from topwards, top view, this is the master surface, and then if your slave surface is something like this here, okay, but this is surface to surface, right? And because this node project down, you can still find a master surface, so the contact will still be established, right? Even though the rest of this area here cannot find the master, but as long as one of it can find, then because this is surface to surface, it will generate that contact. Okay. Right. So there are some cases where it's seldom used, but just to let you guys know, we also have node-to-node contact, right? Why we seldom use this? Because it will be something like this, right? Node-to-node. We can do this if, let's say, one of the file here, like this shell, green shell, and the RBE2 is in one file, and then the C bar is in another file, and then we establish contact between them and read the 2 files in. Okay, you can do this if let's say you separate your parts out differently. Like for example, the bottom part is stored in one file, and then the top part is stored in another file. Then when you read the files in together, there's a interface file that generates that contact. Okay. Otherwise, normal cases, let's say if everything is in just one file, we just connect them together, right? You don't need to do something like this. But if you want to do something like this, we still have that node-to-node contact. Okay, this will establish that contact between them. All right. Yeah. So it's supported for linear. It's supported for non-linear as well. Right. Large displacement is supported, but it will not update during the iteration. Okay, it means that you will establish that contact, but then you cannot separate lah, and during the large displacement. Okay. Right. So has CK, you asked earlier, when do you use slave and master, right? So there are some rules or rule of thumb that we follow when we set master and when we determine our master and slave. Okay, I'll go through that. Right, but now let's see this. Before I go to this, let's talk about that. When do you decide slave and master? Okay, so when do you decide slave and master? If let's say you have 2 objects like this, one is a very small one and one is a very big object. Imagine a table and a ball. So normally the smaller objects will be defined as slave, okay, and the larger objects will be defined as master. Why we do this? Because you might have a lot of slaves, like what you have just now, your PCBs, right? You might have a lot of slaves that is gonna be contact with the PCB board. Okay, so it's easier to define this way because you can reuse that master surface. Okay. Second reason is because it's easier for them to establish contact lah, right? If your slave surface is small, it's easier to find that contact surface, right? To find that master. So having the smaller object has slave is going to be better. Okay. Imagine that if let's say you are using large displacement and the ball here suddenly move to this location, it will still establish that contact, right? So that's the purpose of setting up smaller objects as slave. Okay, that's the first rule of thumb that we follow. Smaller objects defined as slave. Second rule that you can follow is moving object you define as slave. So imagine that, let's say if you have two plates, they are close to each other, but one is static. Okay, one is static, one is moving. Then normally the moving one we define it as slave. Right, the static one would normally be defined as master. Okay, so that's the second rule. And the third rule that you can follow is normally the softer object, we define it as slave. Okay, so softer object we normally define it as slave. So first, smaller object. Second, moving object. Third, softer object. Okay, so those are normally your slave, slave surfaces. Okay, but of course, it's not always the case. You can also switch between them. Okay, depending on whether you can get convergence or not, you can also switch between them, slave and master. Okay, imagine that if let's say this is now my static object, but it's actually softer. My E here is lower, right? My Young's modulus here is lower. It's a softer object. My moving object is a harder object. So how do you define this now? Okay, so the rule of thumb is just a general guide. You can actually always switch between them, right? But that's the normal rule that we follow, right? Now that's how do we decide slave and master, and then the next you also might want to learn how do you define node, when do you use node to surface and when do you use surface to surface. Okay, so if you have large sliding problems, then surface to surface is better. Okay, but then surface to surface is, just to let you guys know, it's actually more expensive than node to surface. Okay, it will use more computational time and resource, but you will produce smoother contact pressure. Okay, so if you want smoother contacts, better contour, better contact between them, then surface to surface is the one to use. Okay, if your slave and master surface has a corner, so let's say my object is a box and I'm going to contact into this master surface here. Okay, if there's a corner here, if you use, let me use another color. Let's say I'm using surface to surface, but my surface for the box, I define it in a continuous surface like this. So this entire two sides of the box here, I define it as a single slave set. Okay, when you do this, we have the corner option that you can turn on in the contact card to tell that there's a corner, and then you should consider that this surface here is actually different from this surface. All right, if you're using surface to surface. If you're using node to surface, then there's no problem. Because node to surface is generated based on the nodes, then there's no problem to it. Okay, and sometimes you might find it easier to converge if you use node to surface due to this reason itself. Okay. Besides this corner option, the other option that I normally would prefer, sometimes this corner option will cause some difficulty in convergence as well. So normally what I do is, instead of defining the two sides here as one continuous slave surface, I would normally break them into two. Okay, so I will have something like this. This is my first slave, and this is my second slave. Okay, so I have two slave sets that will actually try to find contact with the master surface here. Okay, so this is a better way to determine to establish contact, rather than having if it involves a sharp corner like this. Even if, let's say, if your corner is not sharp, you might have something that is varying like this. Okay, I will also break them into two different contacts. Okay, I will also break them into two different contacts. One I put it here, the other one I start it from here. Okay. Okay. So some guide on when to use node to surface and then surface to surface as well, and then what's the default. So you can follow this table as well to see. Basically, surface to surface is supported for all types. So there's unless there's convergence issue, then you probably want to switch to node to surface. Preferably I like to use surface to surface because it gives me a smoother contact pressure between them, right? So yeah, normally use surface to surface. So if we see here, oh yeah, there's another rule. Forgot another rule, the fourth rule of when do you choose your slave and master. Normally, if your mesh size is bigger, that will be your master. If your mesh size is smaller, that will be your slave. Because you want your slave, that is smaller mesh size, to fall within the master surface, right? So yeah, so it's the same rule. So if your part is smaller, if your mesh size is so smaller, then that will normally be your slave. Bigger one will normally be master. Okay, so for this example here, let's check what's the difference between node to surface and surface to surface. Now the bottom is slave, so smaller mesh size is slave, bigger mesh size is the master. They're both objects are same size, right? And then we have enforced displacement that's pushing downwards. Okay, so you see now actually the moving object is actually the considered master here, right? Now if you use node to now let me just track back a bit. So now remember our rule, the smaller mesh size is gonna be slave, bigger mesh size is gonna be master. So that is following the rule of thumb that we set, right? And because of this rule of thumb, you will see that the stress contour here is actually pretty okay. Even for node to surface, right? Node to surface, the stress contour is still pretty okay. Okay, of course, it's not exactly what we want, for example, in surface to surface, because it's definitely a better contour. Okay, here we see that there's some discontinuous, right? Okay, so node to surface will give you this kind of results. Okay, it may not be a smooth contour, right? But if you reverse it, if let's say now the bottom is slave and the top is master, okay, then that will actually violate our rule, right? Our rule states that the smaller mesh size is slave, but now we use the bigger mesh size as slave. So when we reverse that, when we reverse the condition, you see that now the node to surface, you see there is like jagged. Some areas will have contact, some areas doesn't have contact, right? So, but if you use surface to surface, it's still generally okay. All of the elements are still like being pushed down together. But now some areas that I see here, there's, let me see if I can zoom in. So you can see here, some of the areas are not in contact. Those the orange ones are in contact, and those not in contact, you see they're actually not being pushed down. Okay, so so here is that if you use surface to surface, even though your master and slave definition is the other way around, you didn't follow the rule of thumb, you can still get a fairly reasonable result. So all the nodes are still being pushed down, all the surface are still being pushed down. But here, if you use node to surface, then you see this jagged condition already. Okay, because some of the nodes didn't manage to find a master surface, so that's why it didn't have any contact. Right. So we follow the rule of thumb. you are generally going to be safe, even though if you use the wrong discretization here. But of course, that's why I always stick to surface, right? No matter if my rule here I follow or not, I would generally have a better contact pressure, more distributed contact pressure. Okay. So no matter what's the condition, if your master slave are defined correctly or not, you still get a smoother contour with surface to surface. Right? So that's why I always recommend surface to surface. Okay. So imagine just now your question, you have a shell element. You want to generate contact for both top and bottom, right? So imagine this, I generated contact now. I create a set segment. Okay. So don't ask why we call this set segment. Alright, it should be called surface. Right. So if you need to create a contact surface, you right click, create set segments, right? We also have actually another button here, this new under model, there's contact here, but I prefer to use this. Previous version still got bug in 2020. So just right click, create set segments, and then normally I would, let's say I call this master one, right? And then I select my elements. Oh, I didn't show you this also. So, yep. So you need to check your element normals. Okay. So you have to see whether your elements are pointing upwards or pointing downwards, right? So if I display here, now these element normals, they're all pointing downwards. Okay. So you need to after you mesh, especially for shell elements, you always need to check this. Make sure the element normals are all synchronized, right? If you have certain areas that are in the opposite direction, all you need to do is just hit on adjust here to adjust it back. So for example, let me show you if let's say right. So if let's say some of the elements like this, right? When you mesh, sometimes the elements created are like this, right? They are not in the synchronized normals, right? So we need to synchronize them back. All you need to do is just hit on this adjust here and it will adjust it back. Okay. So once this is adjust back, now if I create a contact, it's going to follow the normals here, which is going to point downwards. Okay. So now if I create a element here, right, and select the face and click add, now you see the contacts created are following the normals of the element. They're all downwards, right? Now this is contact that is from this side here. If you want to have contact on this side as well, you will need to create another surface here, right? So let's say now this is surface 2, right? And of course you can choose the same elements, but here you check reverse normals, right? Add this, and now you see the contact is on the other side, right? So you need to do this for shell if your shell has contact on both sides, right? Then of course when you define contact later, one is going to use this master, the other is going to use this master here. Okay. So that's for shell, right? Right. So here I'm going to teach you how to use this auto contact. So as you seen, normally for Optistruct contact we define in pair lah. So we define the master and slave, right? But if let's say you want to just automatically have HyperWorks to search the contact for you and define it, you can try this button here. It doesn't I'm not sure if it works. It will work all of the time, but you can use this if you too lazy to search lah, right? So under model, there's this contact here, right? You click on this lightning button, auto contact, right? So just click on that, feed in the components. I'm gonna select the two components, okay? And then we put in the tolerance here. So the what's the gap lah, proximity gap, okay? So you can put any value here so that you can manage to search and establish that contact surface, okay? What contact type you going to use? Is it going to be sliding? Is it going to be tight? So let's say it is sliding. Then you have seen some other options as well that you can put in, right? This is more for the search distance, okay? And then we're going to establish contact here. This is the set. So there are two ways to generate sets. One is either you use a set, or the other one is we call surface. Okay. Now the name is a bit misleading. If you choose surface, it's gonna actually create that set, right? If you choose segment, it's gonna actually create that surface, right? So don't be confused with this. Just stick with whatever it is. We can change it later on. Okay. It doesn't matter if your contacts are established, are created using sets or segments, right? So if we right click here, you see there's a set and then there's a set segment. Set segment here refers to surface. Set here just refers to set. Okay, there are two ways to create that stave surface or master surface. Either you use set or use set segment. That's all, right? So this one is corresponding to that lah, right? So don't worry, just use the segment here. It's fine. We're using sliding because sliding here is turned on. If you want to choose another property, then you can choose here. Okay. Don't worry about this also because we can also change this later on. Okay. But if you want to have everything done in this toolbar here, then you need to put this correctly, right? Otherwise, otherwise you can also tweak it later on. Okay, so don't worry. Here, most important is we want to automatically create that slave surface and the master surface. Okay, so using sliding, choose the component and then say fine, right? So it automatically search and it manages just that these two are two different parts. That's why it only establish contact in between them. So you can see this is the contact that is generated. Right, so this is the contact that's generated, right? So if you go to the sets here, you see it has created the segments, right? So this is the bottom surface, right? And then this is the top surface, right? And how do they establish the contact? If you go in the contact here, you see it uses the type sliding because we chose sliding just now, right? And then if you see here, the master and slave, the top. Let me just exit this, confirm this first, right? So exit that, and you see the top, the slave is bottom surface. So this one here, the bottom surface, let me just remove this. All right, so bottom surface, okay, is the slave, right? And then the top surface is the master, and is using surface to surface, right? So you can still tweak this if you do not want. If you want to change any of these, you can still tweak. Let's say if I want to introduce some friction, I can just change this to static friction coefficient, put in my friction here if I want. Okay. Now let's just stick to slide first. Right. And that's it. Unless you have further options like what's the search distance and so on. Otherwise, this is actually good to go. Right. This contact is already established. We can actually use this now. Okay. So that's the auto contact. You can try this. After that, we can set this up for a non-linear run. So let me see if the SPC is already defined. Okay, SPC is already defined. some are constraints, some are enforced displacement. So this is in the direction of 3 is actually pushing it down. You can double check on this, click on the loads. Right, so it's actually -5 is pushing downwards 5 mm. Right, so all this top is going to push downwards 5 mm. Okay. And we also have an NL pump that's already turned on, but it doesn't have anything yet. So let's put in a DT here, initial time step of 0.1. Of course, if you want to have NL out as well, that would be good. Right. NL out. Let's choose, say, 10 increment. Sorry, 10 outputs. And then what else do we need? Let's try without NL adapt on those first. And then you can just create that load step. Okay. So change this to non-linear static. For SPC, just put in the SPC that we have. Okay. There's no loading because the enforced displacement is defined using SPC. So it's also grouped under SPC here. Right. So we can just use them all. Then NL pump, I'll just choose large displacement because -5 is quite a large displacement there. Right. NL out. Okay. And let me choose a monitor as well. So I want to monitor the displacement. So to track, see whether the simulation is going all right. So I probably want to track one of these nodes here. It's in a middle node. Okay. Right. So in my monitor file later on, it's going to print the displacement of this node at every iteration. Okay. So it's going to be tracking the third component, the Z displacement, right? So that's the monitor. Okay, the rest are okay. Then let's choose some outputs, right? So let's go and activate global output requests. Okay. Of course, the displacement, stress, strain orders are the basic, right? Oops. Stress and strain. You might want to look at reaction forces if you want, just turn that on. But most important, if you're doing contacts, the best thing to have is actually this, to turn this on here, contact force. Okay, so turn on contact force, then you get to see your contact pressure, your contact, whether there's contact or not that's going on, right? So when dealing with contacts, to make sure that your contact is always okay, always turn on this one, right? Contact force. Okay, and yeah, so you see the cards here created. The rest, I don't think we have anything else. Large displays already turned on. Yeah, so the rest are okay. We can try to run this now, right? So try to run this. Just rename this as different name. And this is upscale engineer. Yep. So I'll just run this now. Okay. Something's running on my background. Okay. Yep, so it's going to solve pretty quick. See from the folder here, it's done. You look at the monitor file. You can see that it always tracks this grid here, right? So this is the ID that you've chosen in the monitor. So always track this. You know that what's the progress of your simulation, right? Because of the adaptive time increment that we adopt, so you can see that even though we request for 10 outputs, we won't get 10 outputs, right? So even the number of intervals in here, NL out, NINT 10, right? We might not get 10 because because of the adaptive time increment. As long as he detects that it is actually easier to converge, it will actually increase the time step. Okay, so that's why if you want specific time steps to output, better to use time here. Okay, otherwise it can be smaller than it will have fewer outputs, right? So as you can see, the increment actually increased a lot because it finds that it's easier to converge. All right. So let's look at the results. And you should let's look at the out file as well. It should be solved without error lah, here. Yep. So let's look at the results. Okay, so we need to have all this. Yep, so we have 10 outputs, but then it won't be exactly at 3 and then at 4 and 5 and 6. I don't think we have 10. 2, 3, 4, 5, 6. Yeah, we only have 6 outputs here. So even though we set the NL out to have 10 intervals, we might not get 10 intervals. Okay, so we can always look at contact force when we are looking at forces at contacts. Okay, so this will give us a better idea on whether we generate the contact or not. Too fast. Okay, so let's remove one of the blocks. See contact established. You can also look at contact pressure to see contact force. Yeah, contact force. Right. So you can see the pressure distribution. Now this is surface to surface. If the smaller mesh size is going to be slave, right? So this is like the ideal condition. Okay. Yep. So that's the best case scenario where we have smaller mesh size as slave, and then it's surface to surface, right? So you can also try and change that to node to surface. You can also try another run. See what happens if you get node to if you use node to surface. It's 2S, right? You can try to change this to node to surface, right? See what happens, right? And you can also reverse the master and slave. Node to surface, let's say. You can also try to reverse under context, right? Reverse this one here. Instead now this is 2 and then this is 1. So you reverse the master and slave. Okay. I can save this as another one. Okay. Right, so you can try that and run and see what happens. And then for this one, you can also open. And let's say now I try surface to surface, right? So you can run this and see what are the effects of changing those surface to surface, and also changing that master and slave reverse, right? So you can try that. I will not go through those examples. Where's my slide? Okay. All right. So yeah, try to use auto contact. Otherwise, you can also use the manual way to create lah. Right. Now, yeah. So this is the example. Say to node to surface or surface to surface example. Then I'll move on to the next, which is adjust. Right. So advanced features here: clearance, smooth, and adjust. Adjust, you can use adjust if you have initial penetration. Okay, so adjust is going to help you, as the name suggests, adjust back your position. Okay, if there's a small gap you want to adjust also, you can also use adjust. Means that the two surfaces supposed to be in contact from the very beginning, but your actual mesh doesn't have contact with each other. Means after you've meshed the parts, there's actually gap, but you want to move you can either manually move the nodes back to touching condition, or you can use adjust to shift those nodes as well. Okay, the good thing about adjust is as we move those nodes, we do not cause any strain to the model, so there is no like initial strain generated when you use adjust. Okay, all right. So here is an example of adjust. You can set adjust equals to 0. If adjust equals to 0, we will search if there's any nodes that are in penetration, we will move it back up. Okay, that's it. Right. So if there's any initial penetration, we'll move those nodes back up to touching condition. Okay, so that's and this is gonna be strain free lah. Means there's no initial strain. Okay, moving back up won't cause any additional stress here. Right, these are zero strain here. Right. But do take note, if you use different discretization, if you use node to surface, then you see the actual nodes being moved. But if you use surface to surface, the nodes location are not changed. Okay, but we just take into account that there's no penetration in the beginning. Okay, so adjustment is just adjusted as a change in the initial contact. That means there is no penetration at the beginning, but the location of the nodes won't be actually moved up. Okay, that's if you use surface to surface. Okay. Now, if you use adjust larger than 0, if you didn't use adjust equals to 0, but you put a larger value here, say 1, we are going to search for both gaps and penetration. So for example here, let's imagine that we put adjust equals to 5, for example. So you'll search 5 mm up and 5 mm down. You manage to search that all these grids here are penetrating. All these grids here are there's a gap. So you search all these and you position them back to touching condition. Okay, so that's if you use adjust equals to a certain real value. Right. Yeah. So another example here of when if we use adjust equals to 0, there's initial penetration here, and then there's an initial gap here. If you use adjust equals to 0, we will adjust back those that are penetrating. Okay. If you use adjust equals to a real value that's larger than 0, then we are going to adjust both gaps and both penetration. Okay, so yeah, this is done in the initial. There's no additional strain caused during this adjustment. Okay, so this is adjust, and this if it's node to surface, right? We can see this physical movement. But if you use surface to surface, you won't see this physical movement. We just make sure that initially there's no penetration and there's no gap, right? right? So yeah, so just take note, if it's node to surface, it's going to be initial change in the model geometry and also adjustment of the grids can be visualized, right? So surface to surface is just going to be treated as just a change. There will be no visualization of the adjustment. Okay. You can also specify adjust to be auto. If you use adjust equals to auto, then we actually use a 5% of the master element size. Okay, so if your master element size is, let's say 10 mm, we'll take 5%, which is 0.5. Right. So yeah. You can use auto as well. Right. If you want to output, if you want to, let's say you have done adjust and you want to get the final output, or you want to get a copy of this adjusted nodes here, you can set this contact param, con param, right? If you use this con param, we will actually print out a bulk data file. So you'll get a .fem of this adjusted grids here, and then you can use this for the next run if you want. Okay, so that like we automatically fix from here towards here, and then output you that file. Okay, this is using this con param here. All right. Right, so this is an example of adjust. Of course, if no adjust, you see there's initial penetration at these areas here. Okay, so once it's adjusted, then you see it's better now. Right, so there's no initial gap or initial penetration. Right. Right, so let me show you adjust. Okay, so you see here there's initial penetration, there's initial gap. All right, so you can use the contact here is already established. All you need to do is just go and manipulate this adjust here. Okay, so you can either use a string value, you can either choose auto or no. Auto will just based on the, remember the master and then the master size, the size here. So let's say, let's just measure this size is about 1.67, 5% of this, okay, will be treated as the value for adjust. Or you can also set your own values here, change this to real value, and then you put in your distance to search here. If it's 0, then we are just going to solve all this penetration. The gap here won't be solved. If you want to fix the gap as well, you might want to estimate this gap here. Okay, so let's just put this as the entire size is 1.67, so probably won't be that much. So I just put adjust 1 here. Okay, so this will fix both gap and both penetration. Okay. Yep. So only node to surface will get to see this this movement here. All right. So if you want to have the con param at adjust grid here as well, we're gonna output that bulk data file for you. After we have moved it, we'll actually save that file as a copy for you to use for further for the next run. Right? So it's con param here. Right, so let's try and run this. Load step should be already set. Okay. Let's check on the loads. Okay, put SPC inside here. Okay, so let's try to run this. Now we've adjusted already. What was this? Adjust equals to 1.0, right? Because there's no NL out. So if there's no NL out, you can manage to solve in one step, you will solve in one step. And because n param also is 0, so you will solve in one step. Rather not do that, let me just do some time step here. Okay, so I'll override it. Okay. So let's look at the results. Right, so you see we have the files created as well. Those that have already fixed, we have fixed it and saved a copy of it, right? So we see that we have saved a copy of the FEM file also. So you need to just open that. So it's just the grids, right? So you need to overwrite the existing grids in your original file. So you can do that by reading it here. So let me try to read this. Now this is the original file where there's gap and penetration, right? I'll read that, import solver deck. This one here. And when you open this, important that you go to ID offset and say overwrite here. So this will overwrite the grids. And this is the safe one, right? This is the final one that is yes fixed. Okay, so important when you read it in, you need to overwrite it. This will actually overwrite the grids here onto the original file. Right. Let's look at that file now. So you see this is the one that's fixed. That was okay. Yeah. Okay, so the initial step you see that it has fixed all the gap and penetration. Right. Yeah, because I don't have NL out, so you need output the final step for me. So important, if you're solving nonlinear, try to have NL pump and also NL out together. Okay, so you need to create NL out as well. Okay, so yeah, that's the adjust. Any questions on adjust? Okay, so you can try different values. I put adjust 1 just now. You can try adjust auto, and if you don't have any adjust, what will happen? Okay. Now the next advanced feature is clearance. Clearance is to set that contact, right? Initial contact, irrespective of what the actual geometry is. So in the actual geometry, there may be a gap, but if you set clearance equals to 0, means that it's already in contact. So it will disregard the actual gap and establish that contact already, right? So you can use clearance equals to negative as well. If it's a negative clearance, that means you have a interference fit, right? So that means there's a fit there already, especially if you're doing bushing and so on. You can use a negative clearance. Okay. So important to note, clearance will override the initial gap. So no matter if, let's say your gap here, let's say this is my part, I have another part here. Initial gap here might be 5. If I set clearance equals to 3, that means now the gap has turned into 3. No matter what the actual gap is, the initial gap I have here, clearance 3, then the contact will be established. If this part has moved by 3 mm, then there's already contact, even though my contact here I set to be 5. Right? Don't confuse this with search distance. This is search distance is to check the beginning, right? The beginning whether there's a contact or not. So yeah, there are two different things: search distance and clearance. Okay. Right, so that's positive clearance. Then you have negative clearance as well. Okay, so negative clearance is normally for interference fit or press fit. Right. Yeah, so don't confuse with search distance. Search distance is contact surface, right? Clearance is a different thing. Okay. So yeah, so example here, if the gap here is a gap of 0.1 mm, if I set clearance equals to 0, means there's already touching with each other at the beginning. Okay, so this one will have, you see there's a contact force here. Okay, if you set clearance equals to 0.07, you will move, means this has to move because the initial gap or the geometry gap is 0.1. It has to move 0.03 before it establish that contact, because these two add up together equals to 0.1, right? Okay, so yeah, clearance will override whatever gap that we have at the beginning. Okay, and of course, if you put a negative clearance, then you're going to have an interference fit, right? So you can see here that there's already contact established because it's like pushing each other. Okay. Yeah. So for clearance, you can set it from here. I'm not going to use this example, but I'm just show you how to set it up. For example, here, right? So if you want to set clearance, all I need to do is, let me try to just move this. Let's put, okay. So let's say if there's a gap here, right? If I want to move, if I want to set a clearance, let's say initially geometry has this gap, but I want it to be touching already. So I set my clearance equal to 0. Okay, so to do that, you can go to contacts and then find this clearance here. So I put clearance to 0, means that you will already have contact at the beginning. Okay, if not, let's say I put 0.05, you'll move halfway downwards before it generates that contact. All right. So yeah, you can try this also. Adjust here is okay, so let me put adjust 0, or choose no here. Okay. So let's try this one. I would save this as a separate file first. Right, it's done. Let me read the file in. Clearance. Okay, so my clearance value was 0.05. The gap was 0.1. Okay. So let's try and look at the contact force. Wait. Contact is already established at the beginning because I don't have my track. Okay, so I'll rerun this. Right, we'll learn about track later. So track will actually update the contact definition at each iteration. Okay. Read the file in just clearance. Oh, sorry, soft and static. Okay, I need to create the inner out cut. Yep, so important to have inner out for nonlinear runs, otherwise it's going to just solve as a static. 10 iterations here. Need to define it here as well. And out. Okay. Let me close this first. Right, so now we have an out. Okay. Now, if you see now at the beginning, there's no contact force because there's a gap of 0.1, but my clearance is 0.05. So as it moves to the next step, then even though you see geometry wise, there's still gap, but the contact has been established because of the clearance, right? Clearance is smaller than the actual gap. Be easier to turn this. Yeah. Okay, so now there's contact already, and now you see the contact has been established. The gap is always going to be constant because in the simulation wise, it's already has contact already due to the clearance. Okay. So yeah. Hope clearance is clear. All right. Okay. Stop this. Okay, so let's go. So you can try clearance with the block is now. You can try clearance with this file. Okay. And then the other advanced feature is smoothing. So smoothing will, as the name suggests, just smooths the contour. Okay, especially if you have if you're using node to surface, or if you're using you have a lot of angles like this. Okay, so smoothing is gonna help you. Okay, this is mainly just distribution of the contact force, right? Yeah, it only applies to surface to surface. Yeah, so condition here does not apply to freeze contact. Okay, you can apply it to adjust and clearance. So yeah, if the surface to surface discretization doesn't give you already that smooth enough contour, you can turn on smoothing, and then you can just choose to smooth which side, whether to smooth at the master side or smooth at the slave side. Okay. So example of smoothing is something like this, where you get a smoother, more distributed contact force. Right here as well. So this is contact tracking, right? There are three options here: small, finite, and continuous. Okay, so for if you didn't set the track, by default it's going to be small, and small tracking means that the contact is established at the beginning of the step, and then it doesn't get updated throughout the simulation. Means if on the step time equal to 0, it found the contact, it established the contact, and it doesn't get updated. Means throughout the simulation you have that contact. Okay, even if let's say the force is large enough to separate the parts, the contact will still be there. So that's small. Okay, when do you use it? Basically, when you estimate that there will be little bit very small movement between your master and slave, which is less than 1 element size. So if that's the case, then you can afford to use small tracking here. Okay. Then contact update is only at the load step, means at the beginning of load step. Let's say if you have 2 to 3 load steps, it's gonna generate the contact at the load step, and it doesn't get changed throughout the loading increment. Okay, so it stays the same, right? Of course, with this contact that doesn't get updated, the computing power will be lesser, so it's going to solve faster. And it doesn't actually solve for large displacement. So here's where we assume that the displacement is going to be small. So large displacement, if you need large displacement, this small tracking will not be relevant really, right? Because if you are expecting a really large displacement. So if you are talking about large displacement simulation, you need to go for finite, right? So for finite tracking, your contact can change, means that the contact area can shift from one region to another region, right? So it's going to get updated every load increment. Every time step you get updated, okay? And of course, with this updating in contact, it'll be higher computing power, right? The most expensive computing power is in continuous sliding, constantly here, right? Continuous sliding. So here it's if let's say you need to get it updated every iteration, okay? What it means is this. If I were to open an out file, okay, so for example, this out file here, right? So if I am using track equals to small, means that the contact will remain the same for all increments, okay? If I use track equals to finite, the contact will get updated every increment, okay? So increment 1 you check for contact, establish that, okay, solve it. Increment 2, then you check for contact again. Okay, so certain areas might have contact, certain areas might not have contact already. So you checks again, update the contact, and then solve it. Okay, same goes on to increment 3 and so on, right? But for continuous sliding, the contact gets updated every iteration here. So iteration 1, it checks for contact, solve it. If it doesn't, if it violates that convergence criteria check, it will go to a second iteration. It will then update the contact again. Okay, so contact, certain areas might be closed, certain area might be open. Means that the contact might be on or off. Okay, and then for each iteration, you do that update. So that's why it's more. It requires more computing power because it updates the contact, it searches and then establishes the contact for every iteration. Okay, so that's why it's more expensive. So that's the 3 level of contact. When do you use them? Of course, when you're talking about small sliding, you can just use small. But if you have a large displacement, then you have to either choose finite or continuous sliding. You can choose continuous sliding if there is a huge difference. Let's say the convergence issue is very large, you cannot solve it, then you can choose to go for continuous sliding because it updates the contact. And let's say you have a lot of penetration, the contact is not established correctly. Some of the nodes on the slave get sticky, right? Like the surrounding areas, the contacts are off, but only one point the contact is still on, and it's kind of sticking to the master surface. Those are the issues that you can face sometime, and you need to update it every iteration. So you go for continuous sliding. Okay. Otherwise, finite should be enough. So I will normally base my contact on whether I am doing large displacement or not. If large displacement, I'll go for finite. And if I run finite and I see that a lot of slaves are still like sticking to the master, even though it's far away, then I probably want to turn on continuous sliding. Or if my contact is there are a lot of penetration, right? There's still a lot of penetration there. I can also try continuous sliding. Okay, so this is the most expensive because it updates every iteration, right? Right. So if you want to have self contact, we also have self contact in Optistruct here. Means that the master and slave are actually the same part. So for example, the best example would be a G clamp. Let me just draw that. So the best example would be like something like a G clamp. Okay. All right. So they are both the same part. You can establish. The other way to do this is to generate a different contact for master and slave. But if let's say you choose the entire surface here has one contact surface, okay, then you can use self contact as well. So for both master and slave, okay, let me choose a different color. Probably it's better. One way, what I normally would do, I will assign this as master, okay, and then assign another contact surface here. Another contact surface here has slave. Okay, this is the best to do. But if let's say you want to have a single definition of contact surface for the entire face here, right? You can also do so. If you do this, then you need to establish that self contact. Okay, so for self contact, you need to turn on continuous sliding, right? You can use either one, either node to surface or surface to surface. Another example is your spring. So if let's say your coil spring, right? If you just select the entire face, it's going to select everything. So the entire face that you select is going to be your contact surface. So you only have one contact surface. If that's the case, then both your slave and master slave ID and master ID will be the same. And then for tracking, you need to turn on continuous sliding. And of course, the discretization can either use nodes or surface is fine. All right. Yep. So here for self contact, you can either put master ID to be blank, or normally I'll choose them to be the same. So I know that I'm using self contact. Right. It's easier for me to see from the input deck later on. I have under the contact, you have both the same ID here. Okay. Right, so that's self-contact. Yeah, so here's an example of self-contact where actually this is crushing down. So you see this crush here, right? So if you want self-contact, because the inner part, inner surface here is one contact surface, outer is one contact surface, and as it crumbles, it has the possibility to contact you with the bottom part, right, or with another layer. So you see here, this way you can establish a self-contact here. Of course, here you need two contacts, one for the outer surface, one for the inner surface, right? But at their respective cards, both the slave and the master is going to be the same ID, right? And you need to turn on continuous sliding. So needless to say here also you see it's actually large displacement turned on as well. Okay. Yep, here's an example of finite. Here, this can be finite, this can be continuous sliding, so it's up to you. If you can solve this with finite, then you don't need to go to the more expensive continuous sliding. Okay, of course, here also you will require large displacement here. All right. Now we go to some contact outputs. As we have learned earlier, one of the most important contact output is actually the conf. Okay, the conf there, right? And when you actually request for conf, basically you get all these options here, force, and then the all these deformation status, whether it's on or off, open or closed or frozen, right? If you want to look at pressure, you need to define it through Pcon. So if your contact is not defined through Pcon, you just use the type, either sliding, freeze, or stick. Then you get contact force. If you want a pressure, right? If you want to look at pressure, contact pressure, then you have to use a Pcon definition. All right. So if you use the friction, if you have friction on, then you see this also, these results also. All right. Yeah, so this is an example of the contact status, right? So for contact status is because you can either have, actually it's a discrete result, right? You either have open, closed, or frozen. But to make it visible in hyperview later on, because we use the legend, right? And a legend is basically a continuous legend. So we have the denomination of 0 for open, 1 for closed, and then 2 for frozen. So even though you see it's a continuous value here on the legend bar here, but you get to know that 0 means that 0 here means that is open. Okay, if you have the value of 1, which is basically red color, right? Red color here, that means this is closed. So contact is established here. If you see a 2, that means it's frozen, right? Same goes to the output for slip and stick. Okay, especially if you have kinematic friction, then you can see this as well. So this we convert the discrete values or discrete results into continuous values here. Okay. Right, and we will learn later on that we can actually apply a energy called contact stabilized energy, contact stabilization energy. Contact STB. Okay, contact stabilization CNT STB, contact stabilized energy. Okay, so when similar to the static stabilization energy, the contact stabilization energy will stabilize the model when you have contacts in the model. Okay, so of course with introduction of external energy, contact stabilized energy is the external energy. When we introduce to the model, we have to make sure that at the end, the energy is very much lower than the strain energy of the model. So by a general rule also is 10%, right? Similar to the similar to the static stabilized energy. As long as the energy introduced is less than 10% of your strain energy, then the model is okay, right? The results in the model can be trusted, okay? So this is the same. We print this under the ENLM file, which you can also load through the energy MVW. So let me show you one of it. So we see here something that we ran yesterday. You see something like energy MVW. So you double click on this and this will plot this plot for you. You plot this energy plot for you. Okay, then you can have a look and see whether your contact stabilized and also your static stabilized energy is below your strain energy. Now, yesterday we didn't use any contact stabilized, so whenever I plot any of this, it doesn't really have that. It doesn't really have that that contact stabilized. Okay, so as long as you don't turn on static stabilize, it won't actually print that static stabilize. If you didn't use contact stabilize, also you won't print out that contact stabilize because there's basically zero lah, right? So far we have not used any contact stabilize, so we don't see anything of that on that. But we have used some static stabilized energy yesterday in the stabilization run of the buckling. So those we get to see the energies there. Okay. Right. So it's actually very important to compare this one so that you know that your results at the end can be trusted. Okay. Sometimes you might want to look at the contact that is being established. So contacts are just formulation. We don't really have the element representation of it. Okay, but if you want to view them, you can still do so. Right? If there are certain areas that cannot establish contact, we'll actually print out a .fem file that tells you that there is no contact established. Right? Contact fail to establish in these areas here. So there'll be the grid numbers, or we actually categorize them into sets, and then you can read in the sets into your HyperWorks and check where are the areas that doesn't have contact. Okay, so there's a separate file. It will only be generated. It's going to be generated automatically, and it will only be generated if it finds that certain area doesn't have contact. Like for example, if your slave area is this big, and only part of here gets to generate contact, we place all these grids here, or all the elements or all the grids under a set that is going to be stored under this here, under .fem. Forgot the name. It's going to be something like no concept. So far we don't have anything on that. Later we can see if we have example on that, right? So the name will be obvious. There's it's going to say like something no contact .fem, something like that. Okay. Right. So that is for areas that didn't manage to generate any contact. Then for those areas that you have contacts already, if you want to view them in the HyperWorks, you can request for this output here. Okay, so you can request for this contact param, con gap output, right? Two methods, you can either use a con gap or con out. Okay, so con gap is only used for node to surface, and it will represent those areas that contact has C gap elements. So you can see something like this, right? So we will generate something like this to denote that there is contact. We don't actually use this C gap element for contact. It's just a representation, right? And if you use the con out option here, we are going to represent it with this RBE3 plotel. So it's RBE3 and then RBE3 at the bottom and then plotel in the middle. Okay, so yeah, RBE3 plotel here. Plotel is just plot element. All right. So again, this element is used to just represent the contact. It doesn't really use it for contact calculation. All right. So yeah, just take note, you can actually turn this on if you want to view contact. Right. Okay. Right. So here is the stabilization energy that you can introduce to stabilize your run, and then of course when your run is stabilized, you get to converge. Right. So if the model is experiencing a lot of instability because due to the context, you can introduce this context stabilized cut. Okay. So there are also a few ways to generate that context stabilized, right? One is to use that cut in specific. You define the cut here, right? Once it's defined, it's going to be used. The other option is to use a param expert NL. So I talked a bit yesterday. There's a param expert NL where we apply yes. Okay. If you apply yes, it just adopt that time time increment adaptation. Okay. If you turn it to context stabilize here, it will activate this context stabilized energy. Okay. So yeah, once you have this context stabilization energy turned on, it will print out the energy that's introduced in this file here, e.nrm, and of course later on you can use the session file to plot it, so you get to see something like this, right? As long as the context stabilized energy that's introduced is less than 10% of the strain energy, then it's okay, right? So the highest is here, strain energy, so it's actually definitely less than that, right? So this is the context stabilized card. Most important thing for this card is first you need to know the keyword, and the ID will take care of itself. The only thing that you probably might want to manipulate is the S0 and S1. So this is a scale factor for the stabilization energy at the beginning of the subcase and at the end of the subcase, right? So your run might get unstable maybe in the beginning, so that's where you want to put a factor of 1. So that's why I put a factor here. So if the stabilization energy were to be introduced, it's going to apply this full factor here, right? Factor of 1. Otherwise, at the end of the run, we want to make sure that the energy is being removed. Okay, so at the end of the run, probably you're going to set it to be 0, or if it is still unstable at the end of the run, you can use a very small value, 0.01, for example. Okay. So yeah, the only thing that probably you might want to manipulate is just this S0 and S1, right? Okay, so yeah, so that's context stabilized. Then we have preloading here. So we touched a bit on preloading yesterday. Here's an example of how we can refer a new subcase to a NL stat, okay, by using this stat sub here. Of course, we learned yesterday there are other methods. You can use the continuous nonlinear sub, right? CNT NL sub. So you can use that also, or you can also use stat sub here, right? Yeah, so same yesterday. Okay, preloading support, we have both discretization, so no problem, with and without friction. Okay, you can use stat sub. Stat sub again will just update the stiffness. Okay, if you want to update the conditions as well, you want the stress, displacement, and strain to carry over, you should use the continued nonlinear sub. Okay. So yeah, stat sub can be used to refer to linear or non-linear static, whether it's small, large displacement, contact, and so on. Right. So example of use case is something like this. First, you might have a large displacement. Maybe like here, there's a large displacement here, and your stat, and then you use then there's also pretension here, and then you use the result here and carry over the stiffness result that's calculated from subcase 1, carry over to subcase 2. Right. So subcase 2 here is a method, so it's calculating for the normal modes analysis, right? But they might have a pretension at the beginning and use the pretension to simulate for the normal modes, right? Example is like, if let's say I have 2 plates here, right? and I have a bolt. Okay, it's bolted. All right. Now there will be a lot of difference whether I pretension this or not. So that's why there's pretension applied here before we run a normal mode analysis. Without pretension, maybe the two, there won't be any stiff connection between the two plates here. Okay. Once there's pretension, then you'll be like clamped together. All right. So that's why it's important to consider pretension, especially if you have bolts, before you run for a normal mode analysis. Running that with and without pretension will be different. Okay. We also have fast contact in Optistruct. So fast contact is an alternative formulation, right? Compared to what we have learned earlier, right? It's going to be, as the name suggests, it's going to be faster. Okay, but it can only be applied if the only non-linearity is just contact. So, and contact with no friction. So if let's say your model has non-linear material, you cannot use fast contact. Okay, you can use fast contact if the only non-linearity is contact, right? Right. So non-linear geometry is not supported as well. That means large displacement also cannot be supported. Okay, so no large displacement, no non-linear material. If your only non-linearity is just contact and it doesn't have friction, then you can use fast contact, right? So fast contact is of course going to solve very much faster compared to the traditional or our traditional contact there, right? There are two ways to generate fast contact. You can either use fast con, yes, or use this param CD iter, right? So this is going to use the MPC base. MPC is, imagine MPC like your RBE2. Okay, so this is the old NASTRAN approach, which we carry over from NASTRAN. You can also use param CD iter. There are two ways to that. Okay, so both will function the same. Sometimes you're gonna get convergence with fast con, then maybe you're gonna try with this CD iter. Okay, that's only when you switch, right? But otherwise, you can use the fast con, yes, and try to see whether you can get accurate results comparing to your traditional or the normal non-linear contact. See whether you can get good results. Okay, so you have to set up as per node to surface. You can use surface to surface, only node to surface, right? And again with no friction. So here's an example of this fast contact here, right? So it's just normal CPU. These are the elements, right? And we compare the full nonlinear analysis with fast con. Okay, so you can see fast con. We have to look at the wall time. So fast con just solved this in 18 minutes compared to 2.5 hours in normal nonlinear analysis. Okay, so yeah, it's going to solve very much faster, right? But again, only if your condition allows. Means that there's no other non-linearity, only contacts, and the contact is frictionless, right? So to activate that again, just to do this, right? You define your contact as per usual using the node to surface approach, and then you use a fast con, yes. Right. Okay, so I'm gonna now jump into setting up contacts for this example here, right? Because we're going to use this later on and also apply pretension. So I'm going to show you how to apply pretension in the next chapter also. So this is the model that we're going to use for the next chapter as well, right? So in the end, you should get something like this. Let's go into Hyperbox to set up this, okay? So this is the model. Right, so what I did, let me just do this again. So I will import the file in. Before this, before we continue, any questions on the contact chapter? If you have any questions, you can just ask, just unmute and ask. I will also just continue on this demo for now, right? So for here, what we need to do is this is the boat, of course, and it's gonna have contact in this area, right? So the boat is gonna be contacted to this yellow part, sorry, orange part, and also have contact with this blue part. And then between the orange and the blue part, we also have contacts, right? So what we can do now is to create those sets. There are some contacts already, but mainly this is contact for this gasket here. Okay, so you see they have contact here already for the gasket. So we only need to set up the contacts for the boat area. Okay, boat area doesn't have any contact yet. Okay, so to do that, let's just try this auto contact. I'm going to see how good it is. Okay, select my 3 components. The setting wise, I'll just leave it as default first because I can change it anytime. Okay, and just say fine. Okay, so we managed to search this contact. Okay, for the bottom, or you can say the nut, right? So this is good. I can accept this. Move to next contact. This is for the top, the boat head. Right, I can accept this. Next. Oh, that's all. Okay, let's accept that first. Wait, let me see the rest. Oh, so he managed to create the other 2 was for the gasket. Okay, so he established contact for the top. So let me review this. Oh, sorry, this is for the bottom. So bottom, right? And for the top. Okay. Now let me double check on the surface created. Okay. Okay, so it generated that surface correctly. Just turn on the bolts, right? So this is for the nut area, and then this is for the top area. But for the top, it's the other way around. Right, so I need to switch this direction. This direction is okay, it's downwards. Okay, this one is upwards, right? So probably only this set here that I need to switch. So okay, let me isolate that, and I bring up my boat. I just need to redefine this one here, right? So I need to use, before that, let me clear this up. Okay, and I will use, so it should always be hours like this. So now the contact looks okay, right? Of course, you can go on and create contact for the shaft as well. Shaft and also for the components, right? Right between here. Let me just hide one of it. You can see here, I should have contact here as well, but I'll just leave it for now. You can try it if you want. But I will define contact between the 2 plates here. Okay. So this one, it didn't manage to capture, maybe because I put it here proximity to be 1.0. So if I measure here, it's actually 2 lah. So let's say if I now try, select the 2 components, put in a, let's say, let's put 2.5 proximity, and between the 2 components and find, it should be able to create that contact. Yep. So these are all the contact areas lah. Okay. So this is good enough. I don't need to do anything. So you can try auto contact. Otherwise, you need to manually create lah. Right click, create a surface, and then come to here, right click, create contact. Contact. Yep. So that's how you need to do it manually, and then assign your properties here. So for now, property wise, I'll just put them all as sliding first, see whether you get converged or not. Or surface to surface, so no problem. Tracking, I would use I think we can try small here, so you won't have any large displacement. Yeah, I'll just try with small. Then try to run this. Okay, so this is only the setting up of contact site. We haven't defined the pretension yet, and so on. So we'll do that later in the next chapter. Okay, so this is just defining contact. Of course, manually, if you want to define, you have to, go right-click, create a surface, and then right-click and create a contact. Okay, and then define your properties inside here. Okay, so auto contact now is good enough to handle this kind of situation. Just now I was talking about smooth here, so I couldn't see earlier because it was hidden. Now this is the smooth. If you need to have smoothing, just need to turn this to 1, or you can have 2. It depends on how many surface you have. Okay, you can have many as you want, because you can choose it to be smooth on the master side, we call it main, or the second side, which is the slave. So you can either choose smoothing on the main surface or on the second surface, or you can choose for both. Okay, once you choose your side, you can also choose the region. So region means that maybe like here, like for my let's go back to 0. Let's choose this one here. Okay, so let me bring them up. Sit. Okay, so let's say for this, for the purple and also the white contact, right, which is actually these two here. Supposed to be this one. Okay, this one. Okay, so for this and this contact, okay, now this better, right? For these two contact here, because even though they are just two ID, but they have different regions, right? So this is like the front region, this is the rear agent, the back region, right? So probably you want to have smoothing on just the front region and not the back region. Then you need to create different sets for them. Okay, I mean, now there's only one contact set. You need to define another area where you only apply smoothing. So let's say I want to apply smoothing on the front area only. So that's why you can have in the contact, you have this option here. First is the side, whether you want to smooth on which side. Let's say if we smooth both master and slave, top and bottom, then you need to choose the region as well. So you can either choose all the region, means both this region here will be smooth, or you can also select another set where you only have one region smooth. So in this you need to define another set that says only, maybe even for the front region, only I want to smooth at this area here. So you need to define another set for that. Okay, otherwise if you want to smooth the entire thing, just use all here. Right, so that's the smoothing that I missed out earlier. Okay, so when you're smoothing now, contact here is already set, so I will just save this for now, because I'm going to use it in the next chapter. Wait, let me see. Okay, so I have contact there. Let me talk a bit on the stabilize. So if you need to turn on the contact, contact stabilize under param expert NL. You can turn this on, right? Contact stabilize, or you can control by creating a contact stabilize card as well. So you can go and right click here, create contact stabilize in the load collector. Okay, so this creates that contact stabilize card. Then you may want to edit these two values here. Factor of contact at the beginning and at the end. Okay, by default is one full. We apply full contact stabilization energy at the beginning, and then at the end we put it at 0. Okay, but if at the end of your run you still find that something is still very hard to converge, then you probably want to add some very small value here. All right. So yeah, you can turn this on. Now we already have the expert NL. Expert NL is by default, so you cannot adjust the values there. But if you need to scale them, you can use this contact stabilized card. Otherwise, the param expert NL will handle that. All right. So I generally like to use param expert NL, let it handle itself. In the end, I just check the energy whether it's okay or not. Okay. Contact is on. Good. So yep, I think this is okay. Let's see what's running here. Okay. All right, so I cannot run this yet because I haven't set up anything. So this is only the contact that's set up. So I'll move on to the next chapter now. Any questions so far on contact definition? Okay, so if you follow the example, he's going to ask you to use a pcon. So it's the same thing. Let me just check what setting they use there. I can emulate it. So there is a pcon, and they apply a friction of 0.2 plus separation, yes. So you can try this. I would probably not do separation, but I'll put that friction there. Okay. So I can update my contacts. And instead of going slide, I probably want to choose a friction coefficient and put 0.2 here. Okay. So it's similar to what we have in the pcon, right? Okay. The benefit of using pcon is you can create a property contact, and then you can assign it to all three of them, right? So since we are here, I'll just show you an example as well. Let's say I create a pcon. I have that. Okay, stiffness, I just put it at auto first. Here I put 0.2 and separation, yes. So now this pcon is pcon ID 6. I can assign pcon to all of these as well. So property ID, assign it to pcon here. Okay, so I can do this also. I can select all of them. Okay, it doesn't allow me. Okay, so I'll just do property ID. I can do 6 here as well. So different ways of defining a contact. Depends on you. If you want to have a generalized contact for all your contacts, you can use pcon. Otherwise, you can go to each of the contact and then manipulate as well. Of course, you can also generate different pcons, right? Which has different friction, whether you can separate or not. So you can have different customization also. Okay. So you can try both, whether you use just the static friction or you're going to put pcon here. Okay. This. Right. Yeah, I guess that's all for contact. Okay, some best practice. Yeah, always try to use contact surface rather than using sets. So using the what we see here. Let me show you from here. Here, if you use the auto function, auto contact function, we automatically create set segments or surface here. Okay, so it's better to use surface instead of clicking create sets here. Okay, create set segments instead of sets. Right, if you use set segments, use a surface. It's going to be better for contacts. But you can also use sets and then use element set, or also grid set for node to surface. Okay, both the methods work, but we see better convergence with contact surface lah. Right? Surface to surface should be used for large sliding. Okay. Here it suggests you to try constantly continuous sliding before going to finite. Okay, because it's more likely to converge. Of course, because it takes more, it's costlier, right? It's more expensive. So I normally will go the reverse. I try to use finite first. If you cannot solve, then I use continuous sliding. Okay, because I want to see my results fast. So yeah, so it's up to you whether you maybe like you don't have the time to experiment. You just go for continuous sliding because it's more likely to converge. Okay, but if you have let's say if this run is gonna be like a benchmark for your future runs. So the future runs will also depend on what are the settings that are set here. Then probably you might want to, or if you have, or this is a initial run which you're going to improve, means you need to improve the design. You need to run a few iterations, a few design iterations. So you probably want to try to solve it with finite first, because finite is going to solve faster. And if finite works for this one, then probably the next one finite will also work. Okay, so that's where you can save some time there. Okay, but if you only have one of the runs, you just want to make sure that this is run by tomorrow morning, you can just try continuous sliding and let it run. So it's up to you whether which one you prefer. I will normally prefer finite first because I want to try to get my run solved faster in the shortest time before I go to continuous sliding. Okay. If you have a contact surface that has a sharp corner, again, remember my example that earlier. Okay, if you have a sharp corner like this, right? This is slave, this is master. Then you two ways. Either you use node to surface, right? Which you then can define all your nodes here under one slave. Okay, and then here all of them under one master surface. Okay, if you use node. Okay, node to surface. If you use surface to surface, then there's a corner option which you can turn on. Okay, corner option which you can turn on. Or you split it into two surface to surface contacts. Okay, so I generally would prefer to split them, right? So that, like, if I split them, and let me see, right? This area here, I'm going to define as one contact surface. And then this area here will be another contact surface. Okay, so the contact here can be turned on. It's going to be independent with the other side, right? So it can be on here, it can be off on the other side, and vice versa. So I would prefer this kind of setup where I split my contact into two separate contact surface. Okay. All right, so there's something for you guys to ponder, and also do remember the rule of thumb, right? When you define your slave against master, slave is normally moving, softer, smaller, and also smaller mesh size. Okay, again, slave is normally smaller in size, smaller in mesh size, is normally moving, and it's normally a softer material. Okay, so if you go by this, then your run should be okay. All right. Now let's move on to integrating the pretension step into our solution. Right. So this is just a typical or a usual use case where we actually integrate pretension or any preloading into our model. Okay, so we touched a bit on this earlier about the nonlinear loading condition, especially if you are dealing with continuous nonlinear sub and so on, right? So we touched a little bit on this yesterday. Here we're going to learn how do we use them. Okay, so pretension is what we're going to focus on. Of course, continuous nonlinear sub and then the time-dependent loading is also available. We can use it. But here is where we going to focus multi-step here. First step is where we apply the pretension, okay, and then we use the result of pretension to carry over into the second step to perform any simulation, any kind of simulation, right? So, right, so it is as we all know, with pretensioning, it's actually a multi-step process where the first step we actually perform the pretension, especially even so in the real world where we actually apply the pretension first. And then the second step only we apply the loading, right? So it's loading is when it's being used in operation or and so on, right? So this with this requirement, we need to separate our steps as well. So the first step is going to be this pretension. There will be no load applied. Second step only we apply that loading, right? So with this, you need to refer with the stat sub pretense here to refer to the subcase where the pretension is being carried out. Okay. Pretensioning can be in Optistruct can be applied either to 1D elements or to 3D elements. So you can model your boat as 1D using a C-beam or a C-bar, and then you can also model it with 3D boats. So if let's say like the example that we had earlier was a 3D boat where we actually meshed the boat with hexa elements, so you can use that as elements for pretensioning, right? So we are going to use something that's built into our HyperWorks, which is the pretensioning manager, to actually help us create that pretension. Right, I'm going to bring you step by step. It's actually very easy to create. Of course, if you look at the cards, you definitely need to create a lot of cards, PT force, PT adjust, depending on whether you're applying force or applying the elongation or the shrinking in displacement to apply that pretensioning. So we can either apply a force, which you need to put in the magnitude, or we can also apply the shrinkage here. So how much the boat shrinks or displaces. Okay, so to apply that pretensioning. So pretensioning can be done in two ways. Again, either in force or in length adjustment. Right. So this is the card for pretensioning. Don't need to be too stressed on the cards here. We normally won't see this. Even I don't also see this. I normally deal with the pretensioning here. So it's easier. This is pretty much easier. Okay. Of course, here you need to create the surface ID if you're dealing with 3D pretensioning. With 1D pretensioning, you need to define the element here. So yeah, two different methods, right? We learn here from here. Either we can define it with element ID or we define it with the surface ID. Okay, so that's the pretense that we're gonna apply. Right, so if you're using force to define the pretensioning, we will create this PT force and then define the pretensioning force. Okay, and then if you're dealing with adjustments, length adjustment or the shortening, then we use this PT adjust. Okay, so yeah. So on the cards, you see something like this, where there's a pretense. It's going to be applied on this surface ID. Surface ID here is actually none other than just this, right? And there is this surface ID will be similar to contact surface. Okay, so here will be similar to contact surface. They are the same type of surface, okay. And PT force here we're applying PT force, so we need to make sure that these two SID here is the same. Okay, set ID here is the same. Okay. And then this pretensioning is being referred to the pretensioning in the subcase level. Okay, so we need to put in the subcase in the subcase or in the load step early, later on. We see that we need to define that pretension. Right. Yeah, so example of 1D pretensioning and 3D pretensioning. So with 1D, as you see here, it's just RB2 and then there's a bar, RB2 bar or beam, and then there's a RB2 at the bottom. Of course, with this, you don't see any context, right? Because these PG elements are directly tied to the parts, so you don't see any. You don't need to define any contact. But for 3D bolt, you need to define contact. Okay, that's what we will be using. We have defined contact earlier, so now we're going to apply that, similar to this case here. Right. Yeah, so there will be difference whether you have pretension or not. Okay, so no pretensioning, you see the displacement is higher. Okay, because there's no pretension here. This part here can dislodge, can be displaced bigger than compared with pretensioning, right? Yep. So you can also export the values out using pre-tensioning bolt, pred bolt here. So you can export this out into a pred file. Then you can look at this pred file is just a text file, so you can just open it with any text pad and then look at the pretensioning force or pretensioning adjustment values in the file. Okay. Otherwise, you can also print this out to H3D, right? Okay, so we can also look at sectioning. So even to extract any sections out, you can also define this section output. Okay, then this can be output to a section result file as a sec-res file. So this is optional. If you want to output out in the separate file, you can do this. Right. One thing with 1D bolt, we actually create this S point here. So S point is where we actually calculate all the forces, pretensioning forces. So this S point here is like an imaginary node. So it will be created during the run. You don't have to worry about this. But there will be S point created, just to let you guys know. Right? And this S point is where we actually extract the results from when we're reading hyperview or hypergraph. Okay. So let's go to the demo now. I'm going to show you how to create that pretensioning for this one. Now, this is the pretensioning force that we're going to apply. So it's about 30 kilonewton applied to the surface there, right? So let's go into that. So in the end, we'll get to see something like this. Okay. Right, so let's pause from the slides and let's go to the model. Right, so okay. Now to define pretensioning, I will first hide these two first, so I don't need the two. I don't need the context as well. Let me hide the context. Okay. And I will also hide half of it because I need a surface that I'm going to apply the pretension. So I will just hide that first because I need to create the surface. I'll like hide this one. And this is where I'm going to apply my pretension. Okay. So go to Analyze, and there's a bolt pretensioning manager here. Right. So just click on that. All right. And then you choose either to add 1D bolt or 3D bolt. So it's definitely 3D bolt here. So just add 3D bolt. And you see here, you either choose a existing surface or create new. So I haven't done any creation yet. So I definitely need to choose create new surface and then select this surface it automatically creates the cut, surface cut here, right? Create. So this is a surface now, right? Then I return, and you see the surface now is created automatically. Okay, so it's pretty easy to use. So you don't need to go and select you don't need to create the surface first. You can just use this to create, right? Now then you need to go step by step from left to right. So the loading type, I'm going to choose force, right? Load collector, I didn't create any load collector yet for the pretense. So I'm just going to create new. So this create the pretense load collector. You see it being reflected here under load collector. Pretense, okay? Then the ID, leave it blank, because I'm going to define my loading here, 30 kilonewton, right? Orientation, we can just leave it blank because it's going to be normal. So I can just leave it blank like that. Okay. So the rest is okay. All you need to do is just define whether it's force or adjustment. Define the pretense cut. You create new, right? Because you didn't create yet. Otherwise, you need to select existing. So just create new, and then put in your load here. Okay. And then, yeah, so that's it. Check on this, click apply, and that is the pretensioning created. Right? So yes, it's as easy as that. Okay. So now, yeah, so that's done. You have pretense here. And all you need to do now with the pretense, you need to define it under the load step. Okay. So any question on pretensioning? That's how easy it is to create that pretensioning. All right. Let me create a load step now. So I need to do two load steps. One is the pretensioning, right? This pretensioning load step will contain nothing else but the pretensioning. So I need to use non-linear static because of the context. Okay, so SPC wise, just choose this existing SPC. Let me see here, SPC add. What is inside here? Symmetry and constraint. Okay, fine. Symmetry is just here. Constraint is just here. 1 and 3. Let me just double check on this. Okay, yep, so it's really constrained. Right, so yep, that's fine. Okay, so go back to my load step. Load step, sort my name. Okay, load step, pretense, SPC add. Load, there's no load because I apply my pretensioning here. So it's a pretense, so you need to define this here. This is a pretensioning step, solely pretensioning only. Okay, step is meant to be referred. So this is the first step where I apply the pretensioning. So this is used later on, not now. Okay, you just need to define pretense here. Then NL pump. Let's try small displacement first. I don't expect it to be any large displacement. NL plus also NL out. Let's create the NL out. Okay. Put in my number of intervals. Let's just put 10. Of course, I can also turn this on. All right. Now define it back at my subcase. Sorry, not here. NL out. Okay. So NL out and a pump. No contact stabilized, the rest no. Yeah, I guess that's all. So The model is okay. Now this is going to be just a pretensioning step, right? We can run this first and make sure the pretensioning works before we set up the second subcase. Okay. Let's have some effect as well. Okay, never mind. I'll let this run first while I set up the subcase for using that pretension. Okay. So now let's just double check contact force is on. Yeah. So I will run this. So pretension is on, right? Okay. Right. So should run fine. Now I will create a load step or a subcase that uses that pretension model. Okay. So for that, the easiest to set up is just run a model analysis. We can see from that. So model analysis, I need the EIGRL card. If you remember from your linear, course, I'll just extract the first 15 modes. Okay, EIGRL first 15 modes, and then I'll create a load step. Create subcase. I'm going to call this model with pretension, right? So this one, change it to normal modes, SPC. Let's choose free. Okay, no SPC, but we choose EIGRL here and stats up here. So you can use pretense as a preload. Okay, so here we use this pretense here. All right. So we can do this where we apply pretension and in the first step, and then now we use it. Okay. Just for comparison, I will create another one. Okay, that is without pretension. Oops. Right, no pretension. Right. And same thing, no SPC, but now I don't have pretension here as well. Just the EIGRL. Okay, so subcase 2 and subcase 3. Right, so let's see pretension run. Yeah, it's completed. So you can see we have a summary here. We apply 30,000 Newton, 30 kilonewton, right? So you can see 30 kilonewton applied here for the pretension, right? Yep. So if you look at the animation, do I have hyperview here? Good. Let's just open the model straight away from here. When? Okay, before that, let me just run the model first. So this one I've created. I'll run this as well. I'll run this as a separate name. And yeah, run that. Okay, so let's look at the initial pretensioning step here. Okay, so pretense from 0 all the way to 1. And you can look at the contact force apply. So initially there's no contact force or 0. And has to be pretense. Okay. Right, so it's maybe cannot see from here. Let me hide one of the components. Okay, so you can see pretensioning that's being carried out. You have contact that is progressively applied. All right. So yeah, pretensioning is working now. Okay, so as a pretension, you can see at the back here where the gasket is, the gasket also get compressed lah, right? So you can see from the gasket here as well. Okay. Right, so pretension is happening. It has tightened or increased the stiffness here. Displacement wise, you can also see it. Okay. So this is pretensioning step only. Now we see if there's a difference in result for the model analysis when we pretension and if we didn't pretension. Okay, so the easiest you can look from the out file. I think the run is completed. Yeah. So run is completed. We can look from the out file. Let's just go. This is the pretensioning step. Yes, done. Then it uses the result for normal mode analysis, right? So subcase 2 is the one where you apply pretension. This is the frequency that we get. Okay, comparing to without pretension, subcase 3. All right. Yeah. So all these are probably the normal modes or the rigid body mode, so we can ignore them. The real one should only start from, I think, mode 7 here. Yeah, mode 7 should be the real modes, actual flexible mode, comparing to mode 7 here. Right, it's a very small difference because the pretensioning is only on one boat, but you do see a bit of stiffness difference there. Right, so let's look from the model. Right, let's load the model. Okay, I'm gonna do subcase 2 here with pretensioning, eigen mode. So this is mode 1. Yeah, this is so this. Oops. Sorry, let's compare to mode 1. Yeah, this is just the rigid body modes. Okay, so the entire thing is moving. It's just the rigid body modes. The first 6, 4, 5, 6. Okay. So the actual mode starts here, mode 7, right? So mode 7 starts at here. Let me just pause this while I open a second window. Okay. Copy this, and here I will turn to subcase 3. Right. So subcase 3 mode 7. This is the mode. Okay. So similar mode shapes, but then they're happening at different frequency. So it's 1.66, 1664, 0.3. Here is 0.1. Okay, so it's a slight difference because this is only one boat, right? But if you do it for the entire model, then probably you'll see a lot of difference, right? So you can look at mode 8 as well. Here mode 8 as well. Mode 8 happens at 1855. Here it happens at 1858. Okay, so yeah, there will be difference to your model, whether you have pretension or not. Okay. Pause. Right, so that's integrating pretensioning step into your model. Of course, you can go on and create other type of load steps. Let's say if I create a now another NL step where I apply the load. So if I do that, I will use NL stat here. SPC wise, maybe the same or maybe different, up to your use case. Load, you can define load there, NL palm and so on. But here, most important, you need to refer this stat sub here. Okay, if you want to use the result of pretensioning for your next loading, make sure you define pretense here. Okay. Again, remember, you use pretension when you apply pretension, but if you want to use that pretension model, you use under stat sub pretense. Okay, so that's the difference. Right. Right. So yes, that is integrating pretensioning into your model. Right. So we also have yeah. So we learned yesterday preloading. Yeah. You just have to be careful of stat sub here. There's a difference between pretense and preload lah, right? So we see earlier was preload. Let me show you guys. Here for the model analysis is model analysis. Stat sub here is preload. Okay, but for NL stat here, the stat sub is pretense. Okay, so remember there is a difference between them. Okay, so if I go back to the difference chart here, if you see a pretense stat sub pretense, it's gonna transfer the stress displacement will be carried over. Okay, so the pretensioning step has I pretense my bolt, there will be stress and displacement, right? So those will be carried over, right? But if I were to use a preload, as in what we saw in the model analysis, it doesn't really carry over the stress, strain, and so on. So initially, there will be no initial stress, there will be no initial strain, right? So be careful with that, pretense and preload, right? But in all cases, we carry over the stiffness. Means that the effect of pretensioning is being carried over, but the result due to pretensioning is not carried over when we use preload. Okay, but modal is the only one you can do. Like, you can only do preload. For modal and frequency response, it's just preload. But if it's linear, non-linear, you can choose. Right, you can choose. You can choose to use pretense where we carry over the results here, which is more accurate. Right. Okay, so back to here. So do try this exercise out. It's a continuous from the previous exercise. First, you create a context. Second, you create a pretension, and then you use a pretension for something else, right? For some other load case. Let me see what we have here. I guess here is just teaching you the pretense, and then just run the pretension step. So you can do one step further. You can create another subcase and refer to this pretension step, right? What I did with the model analysis, you can do that as well. So yeah, preloading. Yeah, so remember, if you use a stat sub preload here, we are just carrying over the stiffness. The stress, strain, displacement will not carry over. Okay. So something to note: context need to be surface to surface here for pretense. Okay. And of course, when you run NVH results, you'll see later on there will be difference lah. Okay, when you have pretensioning done, no matter if it's just 1D pretensioning, you also have effect. Okay. Of course, 1D pretensioning, you might not have contacts from the bolt head to the first part and then the nut to the second part, but you still have contact in between the two parts there. Okay, so yeah, you can consider pretensioning even if you only have 1D bolts. Okay. So this is an example of how do we integrate with modal frequency response. Okay, so we've seen earlier that is with modal analysis, but you can also do the same with modal frequency response, right? So if I just open the model here, or let me just open straight the results. Okay. I'll just show you guys how the model is being set up as well. Right, so this is the model setup. First, there's a pretensioning step, okay, where this is a 1D pretensioning, so the pretensioning is done on all the 1D bolts here, which is actually beam elements, right? And with this, there will be contact between the wheel and also the shaft here, this purple color surface, right? So there's the contact and that's the pretension. Okay, if you look at the pretensioning manager, you see the force is being applied, 10 kilonewton at each bolt, right? Then nothing much, contact are pretty much the same. Then we run this for modal frequency response. Okay, so modal frequency response will refer to the stat sub pretense, the stat sub preload. Okay, we cannot have pretense in modal frequency, so the only thing you carry over is just the stiffness. Okay, so that means around the bolts here is going to be stiffer, and we run this for modal frequency response, right? So for results wise, you definitely get to see the difference with and without. Let's try to load the model in. Right, so this is without any pretensioning initial model. Oh, sorry, not this one. Oh, it's 001. Okay, so yep, so this one is without any pretensioning. Okay, and let's look at the result that is at this particular frequency, 500. Okay, so that's this one. Right, so let's open split window. I'll open this one with pretensioning. Okay. This one we look at subcase 2, 500 Hertz, 500 Hertz. Let's open the stress. Okay, here we open the stress as well. Okay, so see there will be difference in the model. Okay, whether you pretense or not. Let's just check 500, 500 model. Okay, so here the displacement is larger because there's no pretensioning. So it's like the bolts are not being bolted, is like very loose here, right? So you see a larger movement compared to this one. Okay. Of course, with this large movement, then you get a higher stress. So here it's going to be like tighten. So that's why you see a smaller stress there. All right. Yeah, because this is not the resonance. So if you move on to resonance, you get to see different thing. Let's try to adjust the scale so that they are having the same scale. Let me check the resonance first. Let's look at the resonance. Slow. Okay. Let's look at the resonance frequency. 580. Okay. So let's look at 580. What's that? Okay. 580. All right. So this is the resonance 580. Let's synchronize this one. Yeah, probably won't see much. Yeah, so the stress here you see is higher because it's being pretension. So yeah, with higher stiffness, of course, you get to see higher stress, right? Here is still free to vibrate. So you see here it's like it's a loose connection here, but here is a really tight connection. Okay. Yeah. So you definitely get different results if you pretension your model or not. Okay. Yep. So that's integrating your pretensioning step into model analysis. So whether it's be it model or be it a model frequency response, even if you just do a non-linear subcase after this, after the pretensioning, you also will see different results, right? And basically that is all from my side.